So, really, problem number one just requires you simplifying what they gave you. So, what they gave you is the following. And it's going to be helpful, of course, to distribute the A into these parentheses and the -5 into these parentheses. So, let's go ahead and just do that. I'm going to draw these arcs to just symbolize the fact that we're doing that. On the next line, it would be 4A minus A squared minus 5A minus 35. And at this point, we have a 4A and a -5A, so those are like terms. Those can definitely be combined. Now, I'd rather write this expression in such a way that the exponents are descending. So we're going to have that negative A squared first. And after combining the 4 and the -5, it's going to be minus A. And then finally, we will have that negative 35. And that corresponds to answer choice C. So that's how you do with that one. Moral of the story with this one, distribute the A, distribute the -5. Definitely remember that when you distribute that -5, it's going to multiply to the +7, and that's going to be a -35. So you do have to be careful with the signs somewhat. You also might want to consider just putting the term that has the exponent of 2 out front so that you have that nice descending order. And that does indeed show up in the answer choices like that. With problem number two, the best idea is to make sure that all three of those numbers are in a decimal form, because when numbers are in decimal form, it's a little bit easier to figure out, which number is greater than the other and so on. So the fact of the matter is we already have, of course, zero point 0.2 in decimal form. We already have 0.03 in decimal form. But then we need some insight to remember that 1/4 is really equal to 0.25. Now, this is something that's worth memorizing, the fact that 1/4 is equal to 0.25, but also on top of that, you could always use your calculator in case you weren't sure. Converting fractions to decimals, pretty easy if you use a calculator. And the way to do it is to take the top number and divide it by the bottom number. So 1 divided by 4 in your calculator would give you 0.25. So at that point, we can really see which number is greatest, which number is least, because zero point 0.2 is really 0.20. We could think of it that way. So we have 0.20, we have 0.303, and 0.25. So clearly, the order from least to greatest is 0.03, then 0.20, then 0.25, keeping in mind that that's 1/4. And that is why, when you look at it, answer choice G is the answer. Problem number three is a classic standardized math test question that is such that you actually don't need to know what x is, but in this case, you just really need to know what x squared is. And then you can just kind of take things from there. So the original situation is this. And ultimately, they're asking, oh, what's x squared minus 4? So I like to, as I say often in these videos, I like to begin with the end in mind. So this is the end, and we want to figure out, okay, x squared minus 4. Well, wouldn't it be nice if we had x squared? If we knew what x squared was, well, we would just subtract 4 from it, and then we'd be done. So let's go on this sort of mission to figure out what x squared is. And the way to do that is to use this equation, subtract 4 from both sides, and then you will clearly have x squared equals 25. Now, I could solve for x, but we don't have to, because all we want is what x squared equals. And we know that x squared equals 25. So therefore, when we go over here, it's really just 25 minus 4. And that, of course, equals 21. And that is answer choice C. Problem number 4 asks, what percent of the total area of the rectangle lies in quadrant 3? they're kind enough to tell you that this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So that's nice of them, at least. They didn't have to say that, but they give you that nice reminder. I think it's probably going to be a good idea to plot the points that they give. And those points are as follows. We have -1, comma, -2. We have 4, comma, -2. We have 4, comma, 3. We have -1, comma, 3. Now, just for the sake of sort of teaching how to do this problem, I'm going to label these. All right, that way we know which point is what. And let's plot point A first. That's -1, -2. So that's going to be right here. Call that A. And plotting point B, that's 4, comma, -2. Well, clearly that's going to be right here. Plot C, plotting C, 4, comma, +3. So that's going to be here. And we could probably guess the other one's going to be here. We're looking at -1, comma, 3. That is right here. Okay, so what we have is this rectangle here, and we want to know what percentage is in quadrant 3. So in other words, we want to know these sort of two squares represent what percent of the total area of the rectangle. Well, let's find out what the total area of the rectangle is, and we'll just kind of take it from there. The total area of any rectangle is going to be length times width. So the length is, we'll say this way, okay? And the width we'll say is this way. So let's start with the length. The length is 1, 2, 3, 4, 5 over. So the area is going to be length times width. So first of all, it is 5, and then it's going to be 5 times what? Well, 5 times the width. So the width is 1, 2, 3, 4, 5. So it turns out this rectangle is a special kind of rectangle called a square. Okay, so 5 times 5 is 25. So the area of the whole rectangle is 25 square units, whereas the area of just this little part right here is 2 square units. So the real question is, 2 square units is what percent of 25 square units? Now, there's a few ways of doing percentages, but one of them is to do the part over whole equals percent. And when I say percent, that means actual percentage. Like if it's 30%, there would be a 30 right there, over 100. Okay. So the part in this case is 2 square units. That's sort of the often smaller piece, not always, but often smaller part. And then we have the whole, which is, in this case, 25. And that's going to equal the percent over 100. Now the percent is the unknown, so we're going to write X there. And always, always, always put 100 down here. Okay, so that's a way of navigating percentage problems that a lot of students seem to like. So we'll just stick with that. And from here, you could always cross multiply. There's a couple ways of doing it. You can also realize that 25 times 4 would give you 100, so therefore 2 times 4 should give you 8. That's something worth considering. Let's say we chose to do it the more textbook way, and that means cross multiplying. So 2 times 100 would give us 200, and 25 times this x right there would give us a 25x. And then at that point, we divide both sides by 25, and these would cancel, leaving us with x equals 8. And that is the answer, which is answer choice F. Because the change in cost is linear, that means that a slope is involved. A rate of change is involved. Now, when it's the case that you're dealing with real world problems that feature like the XY coordinate plane or linear equations applied to real world problems such as cost and time, it's almost always the case that this x-axis right here. What would typically be the x-axis is your time axis. And then what is the y-axis is usually the cost or something like that. Okay. Now, I find that really helpful to remember. Always think, okay, well, time passing is going to be represented by the x-axis. And that's sort of intuitive because we're used to seeing timelines, and timelines are usually horizontal, right? Where the past is to the left and the future is to the right. Now, they tell us what the cost is at various moments in time. So, for example, in 1985, which we'll say is right here, doesn't really matter where you put it. Let's say 1985 is right here. Well, the cost was a certain amount. It was right here, and we're going to call that 620. And then they say in 1995, 10 years later, the cost of clothing for this family was 1,000. So we're going to make this right here, 1995, and we're going to put this above, and that corresponds with 1,000. Well, why am I plotting these points? I'm plotting these points to remind everybody that this is a linear equation and there is a slope between these 2 points. Now, how do you find the slope? Well, the slope formula says to find the difference in y values and put that over the difference in x values. But in this case, the y values represent the change in cost, whereas the x values represent the change in time. So if we want to find the slope between these 2 points, well, we would put the change in time below. Now we know that that's 10. In fact, the problem even says that. It says 10 years later. Well, that's how much time passed. But what was the change in cost? Well, it went from, Y2 in this case represents the sort of new cost, okay? And that's 1,000. So it's going to be 1,000 minus 620. And that is 380. And that's going to be 380 over 10. So therefore, the slope equals 38. Okay, so that means it's really 38 over 1. You can think of it that way. Now, what does that mean? It's rise over run, correct? So that means for every 1 year over, the cost increases $38. For every 1 year to the right, the cost goes up $38. Okay, so if we want to figure out what was the cost of this family's clothing in 1991, well, that's right here. 1991 is right here. How many years from 1985 is 1981? Well, that is a difference of 6 years. 6 years. And for every 1 year over, it went up $38. So how much did the cost increase in 6 years? Well, clearly that is going to be $38 per year times 6 years. And $38 times 6 is $228. Okay, so that's 6 years gone by and a $228 increase in cost. And that's going to be $228 on top of what we already had in 1985. So if we were to plot the point, it would be somewhere around here. Okay, it would be somewhere around here. So what is $228 on top of the cost that we already had in 1985? Well, the cost we had in 1985 was $620. So when you add $228 to that, it is $848. And that is answer choice B. For problem number 6, I'd say it's important to remember that most numbers are not perfect squares. So we're very used to these perfect squares like 25 or 64 or whatever, where when you take the square root of it, it just ends up being some nice number like 5 or 8 or something, or -5 and -8. So we're used to that, but we need to remember most numbers are not perfect squares, right? If you take the square root of most numbers, you're going to get some crazy decimal, such as the one that they gave you, 9.2371. Okay, so you do need to remember that. Now, apparently, we took the square root of some number, we'll call it x, and we ended up with 9.2371. So it then stands to be the case. It's that 9.2371 squared gives you x, right? In the exact same way that the square root of 25 equals 5, and therefore we know for a fact that 5 squared must therefore equal 25. Okay, so if that's true, well, this is true. Okay, and the bottom line is what we could do is just realize, well, 9.2731, which I'll write right here, 9.2371. Well, that's most definitely in between two numbers. One number is 9, and the other number is 10. And what you could do is the following analysis. You could realize that, okay, well, we know that the answer is what you get when you square 9.2371. And after squaring it, it goes and turns into, 9.2371 squared. I'm just going to write that. After squaring 9, though, that becomes 81. And after squaring 10, that becomes 100. So in the same way that 9.2371 is between 9 and 10 before you square it, well, after you square it, whatever this number is, which we don't know yet, it's x, it's going to be between 81 and 100. Okay. Now, the problem asks the certain number is between what two integers? Well, it's between 81 and 100, but you could also say it's between 81 and 99. Now, just in case you're worried about this 100, it's not 99, I understand that, but just remember 9.2 rounds down to 9. So when you square it, it's going to be like a little bit closer to 81, if that makes sense. Okay. Since 9.2 rounds down to 9, it's closer to 9 than it is to 10. So when you square it, it's going to be, the result's going to be a little bit closer to 81 than it will be to 100. So it's safe to say that, 9.2371 squared is between, 81 and 99. Okay. So that's why. That's my smiley face. Kind of a weird eye, but, it's okay. That's why K is the answer. K is the answer to this problem. Functions tend to be challenging for a lot of students. It turns out that, after practice, they not only become relatively easy, but they might even become fun, dare I say. Now, some of you might disagree with that, and I understand. But nonetheless, we're going to walk through this one. Pretty straightforward function problem, actually. We got -4x cubed minus 4x squared. And at the end of the day, they just want f of -4. Okay. Now, I'm a big fan of using parentheses a lot. And what I like to do is remember, okay, if I'm going to do one of these function problems where it's like x turns into a -4 over here, well, I'm going to rewrite the original function just with a bunch of empty parentheses where x used to be. I just do that first because I know I'm going to be filling up the parentheses with something. And namely, it's going to be -4, right? So we're going to do that right now. -4 goes there, and -4 goes there. I did a little typo. That's a 3. Okay, so we have -4 times -4 cubed minus 4 times -4 squared. So it is the case that it is this entire blue -4 that's being cubed right now. And I'm going to want to attend to that soon. I'm also going to want to attend to this -4 squared. And the reason why I need to worry about that first is because of PEMDAS. PEMDAS. So PEMDAS is the order of operations. Some of you might have learned a different acronym, but this is a pretty common one where basically P stands for parentheses, E stands for exponent, M stands for multiplication, D division, A addition, S subtraction. And the P basically means like if there's an opportunity to simplify something that's inside parentheses, then go ahead and do that first. So for example, if you had something like 3 plus 5 minus 2, well, the P says, square away this 3 plus 5 thing. Okay. If there's an opportunity to simplify something inside parentheses, go ahead and do that first. Then move on to subtraction. In this case, it would be 6, obviously, right? So let's kind of draw an X through that to remind ourselves that that actually has nothing to do with this. So P comes first, but then there's E, and E says exponents. And that basically says if there's an opportunity to apply an exponent, do that before you do anything else, before you do multiplication, division, addition, and subtraction. Well, that is the case here. We can apply the exponent of 3. We can apply the exponent of 2. When you apply the exponent of 3, let's keep in mind, anytime you have a negative number cubed, it's going to remain negative. Okay, I'll say it again. Anytime you have a negative number cubed, it's going to remain negative. In fact, anytime you have a negative number raised to an odd exponent, it's going to turn out to be a negative result. Okay, anytime you have a negative number raised to an even exponent, it's going to turn positive. So that is worth making a mental note of for sure. So, um, so we know this is going to be negative, right? We know it's going to be negative, but what's it going to be? It's like, okay, 4 cubed. What is that? 4 times 4, which is 16, times another 4, which is 64. Okay. Now, I don't want to like do too much, so I'm just going to write this -4. And actually in blue, I'm going to write down what -4 cubed turned into. And what it turned into is -64. We're going to worry about that later. Let's keep in mind this is multiplication happening right here. I'm also going to preserve this -4 thing, and we're going to kind of analyze this. -4 squared is positive 16. I'm going to write that in blue as well, because that's what it just turned into. -4 squared is positive 16. Now we're going to worry about, what's going on the next line. So first of all, we have a negative times a negative, so we know it's going to be a positive, okay? Then the question is, okay, well, what's 4 times 64? So that's 256, so it's going to be a positive 256. And looking here, we got minus 4 times 16, which really is minus 64. And then finally, the answer is just 256 minus 64. Looking at the answer choices, what do we have? That would be 192. And that is J. Boom. That's how you do that one. So they give us a pretty weird looking system of equations, unfortunately. So I'm going to draw that right now. We have x plus 2y equals 4. Now it's possible we might want to use the elimination method for these. So I'm going to stack, the x's over the x's and all that stuff. So we got negative 2x plus y equals 7. Yeah, so I'm a big fan of using substitution when there is, an x kind of by itself with a coefficient of an invisible 1, or a y by itself with a coefficient of an invisible 1. I'm actually going to work with this one. I mean, it really doesn't matter which one you work with, but I'm going to temporarily solve for y, so to speak, by adding 2x to both sides. So we end up with 2x plus 7. Okay, now in case you're confused about that, all I did was add 2x to both sides of the equation, and then I end up with y equals 2x plus 7. So what I'm going to do is just work actually now with these two equations, okay, in yellow, these guys, okay. So I just upgraded that to that. And as many of you know, if you're going to use substitution, all you have to do is plug 2x plus 7 in for this y. So I'm going to keep this in red to keep it color coded. We got x plus 2 times something equals 4. Well, what is that something? That something is 2x plus 7, which comes from here. And now we're just going to go red all the way around. We got x plus, after distributing, it's going to be 4x plus 14 equals 4. 5x plus 14 equals 4, right? 5x because we're combining these, but let's just go ahead and subtract 14 for both sides. It's going to be 5x equals 4 minus 14 is negative 10. So we have, dividing both sides by 5 gives us x equals negative 2. And the only answer choice that features negative 2 as the x coordinate or as the x term is answer choice A. So we are done. Now, some of you might be confused about this one because maybe you're used to doing systems of equations where it's like, oh, x equals something and then y equals something, and it's like this whole algebraic thing. And I totally get that. But I will say that we need to remember that when you're solving systems of equations, I mean, what you're really doing is you're taking a look at this equation, you're taking a look at this equation, and in a way, you're imagining what the graph of this equation would be, and you're imagining what the graph of this equation would be. And the so-called solution is the place where the graphs intersect. So in the case, certainly of these, linear graphs, that's a line if you were to graph it, that's a line if you were to graph it. The point of intersection would literally be a point. It would be a point. And when you solve for x, it's like x equals negative 2. Well, that's the x coordinate of the point of intersection. Looks like the y coordinate of the point of intersection would be 3. But notice how we don't even need to figure that out, right? Multiple choice test. Just choose A. You're done. Yeah, interesting problem with 23. I mean, you're going to have like decent game when it comes to finding the GCF of algebraic expressions featuring, x and y and variables and all that. So let's find out the greatest common factor of these two. So the greatest common factor is a number that goes into both numbers. So this is a number. This is a number. We need a factor that goes into both of these. And we want the greatest of common factors, okay? Now, x squared does not go into both of these because this doesn't have an x squared. It's got an x, but it doesn't have an x squared. But both of these definitely have an x in it. I mean, there's, x times y squared would give us this, and x times xy squared would give us that. Okay, so I'll say it again, x times xy squared would give us that. So x is most definitely a GCF. Okay, so we're going to sort of calculate the GCF. X is part of the GCF, but then you can kind of analyze the y. So notice you just do things like one at a time. Focus on the x's. You can realize, oh, x goes into this and x goes into that. And then as far as the y's go, I mean, we're looking at y squared, right? I mean, y squared goes into both of them clearly. So it's going to be y squared. That actually is the GCF of these two. I mean, there's no ifs, ands, or buts about it. That's it. That's the GCF. Now, apparently, the GCF is equal to 45, right? So it's like, okay. Apparently, this is true, according to the problem. And that means that there's some number times a perfect square, because y squared is a perfect squared, equals 45. So once again, there is some number times a perfect square equals 45. That's the way to think about it. Well, what's one of the factors of 45 that's like a perfect square? Well, 9, right? Isn't 9 a perfect square? So in other words, we could think x times 9, 3 squared, equals 45. Okay. So y could be 3. Y could be 3. Okay, once again, we have some number times a perfect square gives us 45. The perfect square factor of 45 is 9. So what squared gives you 9? 3. So that's how you do that one. That is answer choice E. Yeah, 25 is certainly a unique problem. Just another example of like the sort of unique problems you're going to have to deal with on standardized tests that you don't often get in school. So the bottom line is we've got a, caution sign that flashes every 4 seconds. So, um, imagine the star represents a flash, and then it's 4 seconds, right? And then there's another flash, and then it's 4 seconds, okay? And then there's another flash, and so on. So you can imagine that going on for a while, right? And then as far as the other one, it's like there's a flash, there's that moment where they flash together, but then it's like 10 seconds, right? And then there's a flash and so on. And then it'll be another 10 seconds. So we'll represent that. I mean, that's one way of visually representing what's happening here. Um, I'll just cut to the chase. I mean, the key with solving something like that would be to find the least common multiple. Because if you think about it, let's just think about this right now. The least common multiple of 10 and 4, that's actually 20, right? And let's look at what's happening. I mean, 20 seconds is already represented here, right? Before there's another flash. We'll do this flash over here, okay? 20 seconds is already represented. So let's analyze what happens here. I mean, we would have another flash. That's a star. Terrible looking star. 4 seconds would go by again, and there'd be yet another flash, right? And then finally, another 4 seconds would go by, and there's another flash. And by that time, 20 seconds has elapsed. 20 seconds has elapsed down here. So this represents like the first moment where they flashed at the same time. And then this guy flashes a lot. This one flashes once more, kind of in between. But then they both flash again right there. Okay. They both flash right there. So the key with something like that, where you have this, I don't know what would the word be, uh, synchronistic flashing of lights, or I don't know, trains running by each other at a certain time or something. When you have this synchronization happening, just ask yourself, would it be helpful to find the least common multiple? To find out where they jive again. And then they're going to do it again 20 seconds later, right? So LCM. That is answer choice D. Number 26 is very abstract. This could be an example of the kind of problem where you might want to just like plug in your own numbers and do a little bit of trial and error where you test different values for A and different values for B. Now, unfortunately, what we're going to do is we're going to take the time to kind of go through each um, answer choice, right? So according to um, F is suggesting that that's always negative, right? But it's like, no, right? I mean, A could be 300 and B could be 1, right? In which case this would be 299. Clearly, that is not negative. I mean, clearly, right? So that's gone. Answer choice G. Answer choice G. That is, I'll just fill that in. Negative A minus B. Well, we could have, um, it's all non-zero values of A and B. I mean, clearly we could have like something like negative 10 minus, and maybe what if B was like negative 20 or something, right? Then it would be negative 10 minus negative 20, meaning negative 10 plus 20, which is 10, right? So that's gone, right? We just we just provided a counterexample where it's conceivable that negative A minus B could end up being positive, actually, right? Despite the appearance of it. Um, Assuming that A and B could be any non-zero value, which according to problem number 26, that's true. It says for all non-zero values of A and B. So I'll just tell you, H and J, you could plug in numbers and discover that there's no reason to believe that H and J would always be negative. But let's look at K. Now, K is the answer, but let's look at Y. Okay, so according to K, we have this. Okay, so this is going to be a negative positive number, which means that no matter what, absolute value is always positive, but it's a negative of an absolute value. So it's like imagine you had the absolute value of whatever, and it's like positive, but then it's like negative on the outside. So that's just definitely going to be negative. It's like negative, like unavoidably negative, this first term. Okay. And then it's going to be subtracting a positive number, right? It's going to be subtracting a positive number. It's not subtracting a negative number. Think about a negative number, like -1, subtracting a negative number. Well, that turns out to just be adding, doesn't it? Right? So when you subtract a negative number, it turns out to just be adding. But when you subtract a positive number, that's just subtraction, right? I mean, imagine -1 minus +3. Well, that's just -1 minus 3. And you know what that does? It brings you further down the number line into the negative region. And, brings you to -4, in fact, right? Which is further to the left of the number line than where we started. So when you have a negative number minus a positive number, of which absolute value B is, you're just going to get more negative. More negative. In the same way that you started with -1, you subtracted a positive number, and you ended up more negative with that -4. So that's sort of one way of understanding what's going on there. I think as long as it clicks conceptually, the chances of you being fooled by a problem like that again, drastically low, because you'll start to think in these terms of, you know, this would always turn out to be negative, this whole thing. You'd be subtracting a positive number. What happens when you have a negative number subtracting a positive number? Oh, you get even more negative. So there's just no way this result could be positive. So K is the answer. So problem number 31 requires an understanding of not just perimeter, but also how to work with ratios as they pertain to geometric shapes. Okay. So first of all, we have a rectangle called ABCD. Always going to be a good idea to draw that. All right. We'll put A here, B, C, D. And notice how the order sort of matters. If it's A, B, C, D, well, it goes from A to B to C to D. Now, for the record, I could have done A, B, C, D as well. But what I could not have done is A to C and then, D, B or something like that. So we do need to preserve that order. Now, apparently the perimeter of the rectangle is 96 centimeters. So in my opinion, it's probably a good idea to just quickly get familiar with the formula for the perimeter of a rectangle. Now that would be P equals 2L, 2 times the length plus 2 times the width. Okay. Now, a lot of students at home are probably used to just, oh, okay, what's the length of this? I'll add it to this, I'll add it to this, and I'll add it to this, and therefore I have the perimeter, and that would totally work actually. But if you think about it, what you've done is you've just added the length plus another length, and then a width plus a width, and therefore it's really 2L, 2 times the length plus 2 times the width. So it does make sense. Now, when we acknowledge that the perimeter of the rectangle is 96, well, that means that we could kind of write this equation actually, 2L plus 2W. And then they say the ratio of the side lengths AB to BC is 3 to 5. Okay, so that's AB to BC. Well, it's 3 to 5, and I'm already seeing this rectangle, unfortunately, is not drawing a scale, but just bear with me. So if the ratio of AB to BC is 3 to 5, well, you could actually represent that information by labeling AB as 3 times some number x, and then BC is 5 times that same number x. Okay, so we don't know what x is necessarily, but we know that for every 3 x's, there's 5 x's over here. Okay, that's a way of representing that ratio relationship between AB and BC. Now, of course, if that's 3x and this is 3x, if that's 5x, then this is 5x. But you know what? I don't feel like we even need to label that, because at the end of the day, we could just use this formula. Let's call the length 3x, and we're going to call the width 5x. Okay. So I'm going to replace the L with a 3x and the W with a 5x. Now, simplifying further, we're going to have 6x plus 10x, and then we have 16x equals 96, and therefore x equals 6. Now we do need to be careful, because what they're asking is for the length in centimeters. Now, for those of you at home, just know that always pay attention to the final question. The question is not asking what does x equal. The question is asking what's the length. Well, the length is right here, and that is 3x. So that is going to be 3 times 6, which equals 18, and that is the answer to that one. So that is B. So problem number 32 is such that it could be helpful to recognize that the area of a square is most definitely side squared. So if you have a square and then you have a side length here, well, that side times this side would give you the area. It's also helpful to recognize that the area of a triangle, I'll just say A sub t, that's 1/2 base times the height. So that's helpful information to recognize for this particular problem. And at the end of the day, they say that we have this triangle. It's actually labeled properly. They kind of describe the labels. But at the end of the day, we can just look at the diagram and see how it's, the dimensions and so on. We've got a base of 16. We've got a height of 8. Well, already that's enough information to find out the area of the triangle. So the area of this triangle would equal 1/2 times the base, which is 16, times the height, which is 8. And that would turn out to be 64 if you were to work that out. Now, apparently, this area, according to the problem, is equal to the area of a particular square out there. Well, all we have to do is just recognize that we could take the s squared of the area of a square formula and set that equal to 64. Now, to solve that, you'd have to take the square root of both sides, and in doing so, you got to do this little plus minus thing. That's a good habit to be into. And then we have s equals plus minus 8. However, it does not make sense to have this minus sign because we're dealing with real world physical dimensions. So therefore, the final answer should be that the side length, s, equals 8. And that is the answer to that problem. That's G. Okay, so problem number 33 gives a diagram that looks something like this, although mine is not as nice looking. But here it is. And they want to know, okay, so EH is what percent of AD? Well, first of all, EH is 3.6. And the reason I know that is because this little rectangle here is actually a square. And I know that because the problem said that. If you look at the directions up above, it literally says EFGH is a square. So if this is 3.6, then this has to be 3.6. And we want to know EH is what percent of AD. Well, what is AD? AD is also 12, right? Because if this over here, which is really BC, if that's 12, well, this is 12. Now, when approaching percentage problems, one way of going about it is to consider the part over the whole and set that equal to the actual percentage over the actual number 100. And you can use that format where that in this case would become, the part in this case is 3.6, 3.6 over the whole, which is 12, and that's going to equal the actual percent. Now I'm going to call the percent P, okay, and over 100. And at this point, let me just make it clear that is indeed a decimal. We could actually, from here, we could cross multiply. And in doing so, we would be multiplying 3.6 times 100 and P times 12. So that would result in 360 equaling 12P. And then, of course, we're going to divide both sides by 12, and that would give us 30. Okay. So that's the answer. The percentage is 30. So when they ask what percent of AD is EH, well, it's 30%. So problem number 39 features a trigonometric function that is such that a lot of students really just don't have a lot of familiarity with this kind of stuff. Now, very quickly, I just want to say that the parent function of the function that they gave you, like the normal version of it, is that. And the way to graph that, it's kind of like a vase that goes like that. Now, it is actually the case that it goes forever. Okay, this cosine function, it actually goes forever, but usually when textbooks will present the graph of this parent function, it goes down like that and then up, and this is called a period. This is the most famous like period that they sort of highlight. It's like this vase shape now. Bottom line is the y value you could say is 1. The y value there is -1, and that pertains to the parent function. It's also the case that this x value is typically denoted with 2 pi for 2 pi radians. Therefore, the middle point there would be pi. It's also the case that this is pi over 2 and this is 3 pi over 2. We're not going to worry about that for now. The amplitude of a function like this, a trigonometric function like cosine x or even sine x, which is sort of a different looking graph, the amplitude is the absolute value distance from the center region up to the maximum or down to the minimum. So it's the absolute value distance from the central oscillation, point down to the minimum or up to the maximum. Now, another way of saying it, some books, including some ACT practice tests, will say, oh, it's half the distance. It's half the distance of the max and min. So if you took the max, which is 1, and you subtracted -1, well, 1 minus -1, 1 minus -1 is 2, so half of that is 1, so therefore the amplitude of this is 1. And the amplitude, by the way, is given by the number that's like right in front of cosine x. It's that invisible 1 that's right in front of cosine x that tells you that from the center line it goes up to the maximum. From the center line it goes down 1 to the minimum. It's only a unit, 1 unit down. Anyway, I'm kind of repeating myself. Now, how does this apply to our problem? Our problem says, okay, f of x equals 1/2 cosine 3x plus pi. So it turns out, like I said, the amplitude is to be found here, right? Well, what's the amplitude then? It's 1/2. Look how easy that is. Look how easy that is. That means that this graph, this cosine graph, I understand you're probably wondering what's going on here. This has to do with horizontal shifts and period changes and things like that. We're not going to worry about that. But basically, that means that this cosine graph, as it goes up and down and up and down and up and down forever, it never gets higher than 1/2. And it never gets lower than -1/2. The peak of the mountain is 1/2. The valley gets only as deep as -1/2. That's what the amplitude means. So the answer to this one is B. The first thing you're going to want to take note of in problem number 40 is that every license plate is composed of 6 characters, okay? Now, according to the problem, the first 3 characters are any letter from A to Z, and according to the problem, the last 3 characters are any number from 0 to 9. And with regards to these, and these actually, in the sort of last part of the problem, they mention that repetition of both letters and digits is allowed. So that's actually very important. The way I like to approach these problems is I draw these underlines, as I've already done, representing the various characters of the license plates. And then I just look at one at a time and ask myself, okay, how many possibilities are there for this one? Well, there would be 26 possibilities with regards to what this is going to be. It could be any of the letters. And I would ask a similar question to each underline. So 26 possibilities for that as well, 26 possibilities for that as well. And now moving on to numbers, and we want to be very careful. Every number could be any digit from 0 to 9. So that's actually 10 possibilities. Think about it. You've got 1 through 9, and then you have 0, right? So that would be the 10th possibility. So yeah, 10 possibilities here, 10 possibilities here, 10 possibilities here. And then all you have to do is just multiply straight across. Now, you could go ahead and, be tempted to do this in your calculator, but you're going to get some very large number actually. And when you look at the answer choices, you'll see, oh, well, it looks like the answer choices, don't really look like they're written as a normal looking number. So we're probably just going to have to conceptualize this situation as something else. And it's true, because in reality, this whole thing right here is 26 cubed, and this thing right here is 10 cubed. So in reality, I mean, we're just dealing with, do a little divider, we're just dealing with 26 cubed times 10 cubed. And in a way, that's the answer. But, when you look at the answer choices, that doesn't quite come up. But if you look closely at answer choice F says 10 cubed times 26 cubed. Well, that's the answer, because multiplication is commutative. It actually doesn't matter what order I multiply this number and this number in. I could just switch the order if I want. Now, some of you at home might be wondering what the heck's going on with all those exclamation points, and we could briefly talk about that before moving on. For example, let's see. All right. I'll just keep it simple. Imagine we had 26 factorial, and that's what that means. They call that a factorial. Now, for those of you who don't know, what that really means is it's um, a code for 26 times the next number down, which is 25, times 24 times 23, all the way multiplying to 2 times 1, and then you'd be done, okay? So 26 factorial is literally the product of all these numbers all the way down to 1, okay? So I do little dots here representing the fact that there's a lot of numbers in between there. I don't really have room to do that, but you get the idea. Now, that's a big number. If you plugged it into your calculator, I'm not really sure what would happen. Maybe it'd be an error, or maybe it would pump out a really big number, one of the two. But and you might be wondering, well, how does this relate? How does this like exclamation point looking thing relate to these kinds of problems? Well, I'll just tell you, I'll give you a heads up for the future. Imagine you had license plates composed of um, 3 characters, right? Composed of 3 characters, and they all had to be, all of them had to be A through Z. But you were not allowed to repeat. Well, think about what that would be. That would be 26 possibilities for this one, but once you've chosen this one, we only have 25 possibilities left here. And once you've chosen that one, we only have 24 possibilities left here. So you can kind of see how this is beginning the process of a factorial type situation, okay? Now, in reality, one kind of fancy way of writing this scenario right here is that it would be, we could say 26 factorial over 23 factorial, okay? Now, I understand if you're wondering what the heck is that, okay? What I'm saying is that this actually equals that, these 3 things being multiplied together, and the reason is because it would be 26, over 25, and then you'd have your 24, right? And then you'd have your 23, and then it would go 22, right? And so on, right? Let's do a little dot, dot, dot. And down below, it would be this, which is 23 times 22, right? Dot, dot, dot. But notice how these yellow things right here match, so those could actually cancel. And that's one reason why you could actually represent this scenario as one of these fractions, because in reality, what this fraction is doing, another way of saying it is it's 26 times 25 times 24 times 23 factorial, right? Because 23 factorial is 23 times 22 times 21 times 20. So you could actually kind of save trees and paper and pencil ink and power on your iPad by just writing 23 factorial there. And then we have the 23 factorial down below right there. And then, you could think of it as these canceling, leaving us with just that. So in other words, this sort of scenario would always produce this scenario. So in other words, if the ACT was saying, we have license plates composed of 3 letters, none of which can repeat, how many possibilities do we have? Well, I don't know. They might present this as the answer choice, right? And that would actually be the answer because the 23 factorial cancels with that 23 factorial, and you're left with just these. I think you probably get it. Hopefully you get it. You could always rewind this and watch it again if you have to. But one thing I would definitely do for sure, regardless of the problem, is I would draw the underlines and I would just simply list the possibilities for each character. Okay, so hopefully that makes sense. The answer to this problem is F. So problem number 41 requires an understanding of frequency tables where before you even tackle this problem, you need to understand that what this means is that there are 3 scores that were between 96 and 100. There's 1 score that is between 91 and 95, 3 scores that are between 86 and 90. And at the end of the day, they even mention, they're kind enough to mention to you that there are 20 quiz scores, okay? 20 scores. Now, they didn't have to do that. You could have known how many scores there were by simply adding all the numbers in this column, and that would be 20, okay? And I would also say it's probably helpful to imagine these scores as listed horizontally like that. Now, you don't actually have to do it, but you could imagine, okay, well, there are 9 scores that are between 76 and 80 over here, and then there's 4 scores between 81 and 85, and so on. Just kind of get a sense of what that might look like if you were to list all 20 scores from least to greatest horizontally. I've always found that really helpful because at the end of the day, this problem is asking about the median, which is the middle score. So you can imagine you have all these scores over here and then all these scores over here, and the median would be the middle score. Now, since there's 20 total scores, since there's 20 total scores, um, the median would be the average of the 10th and the 11th score. So you can imagine, I'll even draw, imagine each of these is a score. That's 5, 6, 7, 8, 9, 10. And then each of these is a score. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the median would be the average of these two. Okay, the 10th and the 11th score. Okay, so how does that help us when it comes to this frequency table? Well, what we could do is we could start down here. We know the first 9 scores are between 76 and 80, and then just count up until we get to around 10 or 11. Now, once we go from 9, um, we go up here, and there's 4 scores between 81 and 85. So that already captures, how many? 13 scores right there. So here's the first 9 over here. And then we go all the way up to 13 over here, and apparently these 4 are between 81 and 85. Now, you don't have to necessarily draw it every time in order to solve this. You just need to understand that this is what's happening. So you have the first 9, and then you go up to 13. So clearly, the median score is somewhere here, okay? It's somewhere in these 4 scores right here, okay? So that is the answer. So we're 81 to 85, so that's answer choice D. Okay. Once again, you don't have to necessarily draw these, but you do have to have some sense that something like this is what this is pointing to, and this represents the first 9. Okay. So hopefully that makes sense. Okay, so let's see. They give you the formula to convert um, Celsius to Fahrenheit, really vice versa. So here that is, kind of a famous formula, you could say. And then they say there is one value of x for which x degrees Fahrenheit equals x degrees Celsius. So in other words, um, x degrees Fahrenheit actually equals x degrees Celsius for a certain value. So there's one special number where this thing actually equals this thing. And that's really the trick. You have to understand that uh, the degree measure of Fahrenheit and the degree measure of Celsius is such that they're related to each other through this relationship. Okay, so you could use this relationship to simply find that number, where there's one number where this is going to end up equaling that. So how do you solve that though? Well, one thing I like to do is just get rid of annoying denominators like this 5 over here. And a good way to get rid of annoying denominators is to multiply the entire equation by that denominator. Now, of course, on the left, we're going to have 5x, and over here, we're going to be distributing. But when we distribute the 5 over here, it's going to cancel that down below. So we actually end up with 9x there because the 9 on top is left over, but the 5 canceled down below. And then we end up with adding 5 plus 30, or 5 times 32. Now, 5 times 30 is 150 plus 10, so it's going to be 160. And then, well, we could go ahead and subtract 9x from both sides. We're going to have a negative situation, but that's okay. We have negative 4x equals 160. And then dividing both sides by negative 4 would give us negative 40. So that is the answer. So apparently, negative 40 degrees Fahrenheit is the exact same actual real world temperature as negative 40 degrees Celsius. So that's kind of interesting, actually. And the correct answer, therefore, is B. I think the key with problem number 46 is to not get overwhelmed by the fact that there's mixed numbers, first and foremost, and also to not get overwhelmed by the fact that we're dealing with ratios. Um, when you're dealing with ratios, that often means that you're dealing with a proportion, and that is actually what's happening here. Now, apparently, there's a bread baking recipe that is composed of yeast and flour. So it doesn't really matter what I put on top, but I'm going to put the Y on top and the F down below. So we will be analyzing yeast on top and flour down below. Once again, I could have put flour on top and yeast down below. As long as everything is consistent across, this should work, what I'm about to do, okay? So we're then going to analyze the information that they give us. First piece of information is that there's 1.5 teaspoons of yeast for every 2.5 cups of flour. So that means there's 1.5 up here for every 2.5 down below. Now, I understand we have mixed numbers within this fraction. That could be kind of weird. We'll deal with that later. We could always convert those to improper fractions if need be. And then we have that equal to something. And what they say is Diana will use the entire contents of a packet that contains 2 1/4 teaspoons of yeast. So already, I'm going to say, let's put that up here, 2 1/4 teaspoons of yeast, and that's going to be related to, a certain amount of flour, and I'll actually just call it X. That's fine. Because according to them, it's in the same ratio that they had mentioned before. They literally say that. They're like, oh, she will use the same ratio of ingredients called for in the original recipe. Well, here's the ratio of ingredients called for in the original recipe, and we're going to use the exact same ratio, which means it's going to be proportional, okay? Which means that this over this should equal this over this, okay? Well, at this point, maybe convert either the mixed numbers to improper fractions, or if you don't like improper fractions within fractions, you could always convert it to decimals. I'm actually going to say let's convert it to decimals, even though that's kind of weird too, to be honest. So we have we have 1.5 up top. That's from this one over 2.5 down below. And then we have 2.25 because hopefully it's clear that 2 1/4 is equal to 2.25, and that's going to be all over x. If we were to cross multiply, it would be this times that, and then we would have 1.5x equals 5.625. And when we divide both sides by 1.5, that would be 3.75. And that corresponds with 3 3/4. So 3.75 is really 3 3/4. Now, if you're not clear about why that is, just remember that this is really 3 75 over 100, correct? So hopefully that's clear. 0.75 is really 75 over 100, and that itself would reduce to 3/4. Okay, if you were to reduce that. So that is the answer. It's x equals 3 3/4. So if you use 2 1/4 teaspoon of yeast, that would correspond with 3 3/4 teaspoons of flour. Okay, so that is answer choice J. Boom. Look at that. So problem number 47, I mean, most people when looking at it, they would see, oh, well, there's probably a way to cancel something out from the top and the bottom and all that stuff. And they would be right because um, this is a rational, well, rational expression, let's just call it that. And we got 3x squared down there. So it's most definitely the case that there's a GCF that can be factored out of the top right there. So we're going to sort of analyze that right now. Now, when you're trying to figure out like the GCF of two terms like this that are sort of complicated, I mean, there's a lot of stuff going on. You might want to focus on the numbers first instead of like thinking about the variables just yet. I mean, you don't want to do too much at once. So it's like, what is the GCF of just 12 and negative 9? I mean, GCF of that is 3, right? So you just put a 3 there because you know you're going to write a 3, right? I mean, the GCF, you're going to factor it out. So there's your 3. Now let's focus on x to the 6 and x squared. So if you're dealing with like x to the some exponent and x to another exponent, the GCF is always going to be the x to the smaller exponents because x squared times 1 gives me x squared. X squared times x to the 4th gives me x to the 6th. So clearly the GCF is x squared itself, okay? So if you didn't follow that, just remember when it comes to the GCF of x to the some exponent and x to another exponent, it's going to be the one that has the smaller exponent. That's going to be the GCF. So we're going to factor that out, x squared. And then it's going to be parentheses, because I know I'm going to write that. I know I'm going to write parentheses here. Uh, and I'm going to put stuff in there. Now, I'm a big fan of just writing the parentheses because you know you're going to write that anyway. And it's going to be all over 3x squared. Now, already we can see, I mean, it's going to be amazing because these are going to cancel, right? So I'll just leave that there in the canceled form because we know we're going to do that. So really, it looks like the answer is going to be whatever the heck is inside the parentheses. Now, this could be confusing. Maybe just work with the numbers. It's like 3 times what gives me 12? Well, 3 times 4. So just put a 4 because you know that that's going to be part of the first term. And then you can ask yourself, okay, x squared times what gives me x to the 6th? Well, that would be x to the 4th. And then 3 times what gives me a negative 9? Well, that would be a negative 3. And then you could ask yourself, x squared times what gives me x squared? Well, that would be a 1. Now, I do not have to write that 1 because 1 times negative 3 is just negative 3, so we're going to leave it alone. And looks like this just turns into, I'll keep it in blue, 4x to the 4th minus 3. And that is answer choice E, it looks like. And that is correct, E. Okay, so matrix stuff is weird if you've never done it before, okay? Um, you know, it's one of those things where once you practice it, you get the hang of it, of course. Let's just be very clear about matrices in general. I'm not going to get too much into what they're used for or any of that stuff, but just know we can say matrices are arrays of numbers, okay? I'm going to use the word array. I kind of like that word there. They are arrays of numbers, okay? And let's say we have this matrix here, we have this matrix here, okay? Now, it is the case that with matrices, they have dimensions, okay? And the dimensions are always in accordance with row by column, row by column. Now, this has 2 rows. Now, rows are horizontal, so it's 2 rows, right? 2 rows by 2 columns in this case. Columns, in my opinion, are a little bit easier to remember. You could think of those Greek temple columns, right? Those Greek columns, they always go straight up and down. Now, with regards to this one, there are most definitely 2 rows, and there are 3 columns, okay? Now, let's say your teacher or the ACT test asked you to multiply these, okay? multiply these? Well, whenever you're being asked to multiply matrices, the first question you should ask yourself is it possible to multiply these? Okay? Because if it's not possible, then the result would be undefined. Okay? If it's not possible to multiply these in the first place, that really just means the result would be undefined. Okay? Now, some of you can already see where I'm going with this. The question literally asks, which of the following matrix products means multiply, is undefined. Okay? So now the question is, well, how do you know if it's possible to multiply two matrices together? Well, you know that it's possible to multiply a matrix like this times a matrix like that as long as these numbers match. Okay? And I think I'll just leave it there. If these numbers on the inside match, if the columns of the first one is the same amount as the rows of the second one, then it is the case that you can multiply this times this. Now, let's be clear though, let's be very careful. Notice how the order matters. What I mean by that is, do you see, I'll just erase all this. Do you see how, the first one is 2 by 2, right? And the next one's 2 by 3. And we just discovered, well, yeah, we could totally multiply these. But you know what? If this one was listed first and it was multiplied times the other, by 2017 thing, that wouldn't work, right? That wouldn't work because what you'd have there is a 2 by 3 matrix times a 2 by 2. And in that case, these would not match. So this might be the first time in your sort of math life where you can multiply something if it's ordered in one way, but if you switch the order, you actually can't multiply it. So that is worth noting. So the order most definitely matters. So all you have to do is pay attention to the answer choices and just ask yourself, okay, well, with the answer choices, first of all, there seems to be a letter that is corresponding with any of those matrices. The first one is assigned the letter W, the second one is assigned the letter X, and so on. Well, let's see which one would cause an undefined scenario. Well, looking at answer choice F, that says WX. Well, W is a certain dimension and X is a certain dimension. W is a 2 by 2 and X is also a 2 by 2, and it's most definitely the case that these two match. So therefore, WX could indeed be a product, a defined product. So now let's look at WY. Well, WY is, once again, that's 2 by 2 over here. And then you have, looks like it's 3 by, oh no, that's actually 2 by 3, isn't it? Yeah, 2 by 3. So that actually could work too because these two inside ones match. And then we have, looks like it's H we can inspect. That is YZ. YZ. And looking at the dimensions of Y, we certainly have 2 by 3. Looking at the dimensions of Z, we have 3 by 2 columns, and these match. So that product would be defined. And then we have XW, and the dimensions of X are 2 by 2, and the dimensions of W are also 2 by 2, and that product would also be defined. So we know by the process of elimination the answer is K, but let's just look at it anyway for our own satisfaction. We have XZ, and X is 2 by 2, and z is 3 by 2, and we can clearly see these do not match, right? The two columns in matrix X does not match the 3 rows in matrix Z, so therefore that product would be, quote, undefined. So that is the answer, because they want to know which one of these products would be undefined. So that is the least you need to know for that one. Problem number 49 turns out to be easier than it looks once you know how to transform parabolas. So the parent function of a parabola is as follows. Let's call it f of x equals x squared. So really all you need to know is the following information, where the parent function is just a regular parabola that looks like this, and it goes on forever like that. And at a certain point in time, you either have or you will learn that you can apply various transformations to this. For example, you could say x squared plus 2, in which case it would shift everything up by 2 units. You could say x squared minus 2, in which case it would shift everything downward 2 units. But one of the famous transformations that you can apply to the parent function is to stick a number other than 1, because right now there's a 1 times x squared. You could stick a number other than 1 in front of the x squared. Let's try something like 3x squared. So now we have 3 times x squared. So basically, this would be the parent function. The red one would be the green one, except we have this 3 in front. So what does that do? Well, basically what that does is stretch all the heights of the points composing the green parabola. It stretches those heights upward by a factor of 3, okay? So what do I mean by that? Well, you can imagine there's an xy coordinate to this point here. Let's just focus on this point here. Well, when you multiply x squared by 3, what it does is it takes the height that it used to be, the y coordinate that this point used to be, and multiplies that y coordinate by 3. So now the height of that point is 3 times what it used to be. Okay, so we could say the y coordinate, also known as the height of that point, is now 3 times what it used to be. So it's this stretching upward moment. Notice how in the green parabola, the y coordinate of the vertex is 0. So when you multiply 0 times 3, that just remains 0. And that's one reason why this red parabola remains situated at the vertex. Uh, it's interesting to kind of note that, yeah, it's being stretched upward, but it most definitely gives the appearance of being narrower as well. So the green seems to have narrowed. I don't really like that description. I prefer thinking of the green parabola as having been stretched upward. Okay, so that is what this number does. It is a vertical stretch. Now, some of you might be thinking, what about if you did something like this? What if you stuck a fraction in there? Well, the fraction would do the same thing in a sense, that it would be 1/2 times the height. Before it was 3 times the y coordinates of each point, but now it's going to be 1/2 times the y coordinates of all the points in the parent function. So this would give the appearance of smushing the green parabola down like that, where once again, let's focus on the parent function. Imagine this point right here. Well, it used to have a y coordinate of, a certain amount, that height, but now that height has been diminished by half. Okay, so now the height of this point right here is half of what it used to be. So basically, it's smushing the parabola down. So that's what a fractional coefficient will do to the parabola. Now, again, some teachers and some people might talk about how it gives the appearance of the parabola being wider, and that's most definitely true. But again, in my opinion, it's more helpful to think of this green parabola as having been smushed downward. Okay, all the points have been smushed downward. So that is what the coefficient in front of the x squared does to a parabola. Now, I do want to just make a mental note. There's another thing, I'll call this ix. There's another thing that the coefficient denotes when it comes to the graph of a parabola, and that is that if it's negative, for example, if it was something like negative 2x squared, well, the fact that there's a 2 means the x squared, means the parabola would most definitely be vertically stretched. But the fact that it's a negative means that it would also be reflected across the x-axis. So basically, you can imagine the green parabola, which corresponds with the parent function, being reflected across the x-axis and being stretched at the same time. So that would give the appearance of something of a narrow looking upside down parabola. Okay, so when it comes to problem number 49, it turns out that really these are the only aspects of transformations that you need to know to solve the problem. So when you look closely at the parabolas, what you see is um, the bottom parabola, which is sort of the widest parabola, is associated with n equals 1. The medium one, which is certainly narrower, also known as stretched upward, has an association with n equals 2. And finally, the most narrow parabola, also known as the most stretched upward parabola, is associated with n equals 3. So clearly we could see that as n increases, this parabola gets stretched upward. Well, that corresponds most definitely with sort of the relationship certainly between these two, where you had a parabola, but then the coefficient just increased, n just increased. So clearly n must be the number that's in front of x squared, and that is why A is the answer. Okay, let's look at D and E. Now D and E have a negative n, or we could say a negative coefficient in front of the x squared, and that would result in a reflection across the x-axis. So those are easy to get rid of. Answer choice C has an n that's being added to x squared. Well, that's a vertical shift upward. That's not a vertical stretch. Okay, that's a vertical shift upward. So that's not a vertical stretch. Answer choice B would suggest that as n increases, the fraction would become less and less. Because if you think about 1 over n, think about 1 over 2. Well, that's 1/2. And then let's make n a little bigger, so n becomes 3. So that would be 1/3, right? And if you notice, 1/3 is actually less than 1/2. So answer choice B is wrong for that reason. As n increases, the parabola denoted by answer choice B would actually get more and more smushed. So I'll say that again. As n increases for answer choice B, as the denominator of that coefficient increases, the fraction would actually get smaller if you think about it, because 1/2 is greater than 1/3, which is greater than 1/4, and so on. So answer choice A is the only one that makes sense for all of the previously mentioned reasons. So for problem number 49, we are looking at A. Problem number 50 is one of those problems where it might be a good idea to think in terms of a Venn diagram. Now, here's a Venn diagram. And this circle on the left will represent students who play guitar. So I'll just write a G for guitar, and the other one would be a P for piano. And what they say is, oh, there's 20 total students, and some of them play the guitar, some of them play the piano. Now, I think it's probably possible that there are some students who play neither. So therefore, I'm going to wrap this in a box, because there might be some students over here who don't play guitar or piano. So that's the first thing to quickly notice. And yeah, so apparently 8 students play guitar. So we know that this thing is going to have 8. It's going to have 8 students, right? And over here, we're going to have how many students? 9 students play piano. So you can imagine there being 9 students here, okay? And given that information, what's the minimum number of students in this music class who play both guitar and piano? Well, we want to minimize how many students are in this intersection. My first question is it possible there's literally no students in this intersection? Let's ask ourselves that. I mean, it might be, right? I don't know. Let's imagine that. Let's imagine there's 8 students over here who play guitar, right? And in fact, I'm going to draw it. I'm going to draw dots. We have 8 students, right? 8 students who play guitar. And we have 9 students over here. 9 students who play piano. And so far, that's 17 total students. We got 8 over here. We got 9 over here. I mean, who's to say that there aren't the additional 3 students over here, right? There's no reason to believe that every student in the music class, okay, there's no reason to believe that they all play either guitar or piano or both. So I'm going to say the minimum number that could be in this intersection, the minimum number of students who play both guitar and piano, interestingly enough, is 0. And that is answer choice F, and that is the answer. Problem number 51 is a really interesting and unique problem that can be difficult to know where to begin. Now, the bottom line is we know that each student, there's 18 students, each student is assigned a number 1 through 18, and we know that when the students are paired with each other, the sum of the pair should equal a perfect square. So let's be clear on what some of the perfect squares are. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So it's just good to get familiar with some of these, okay? Now, the perfect squares are all of these numbers here, right? All of these numbers right there. Now, since the highest number is 18 and the next largest number is 17, when you add those two, you get actually 35. So even when you add the two largest numbers, you're never going to get to 36. So therefore, we could actually ignore 36 as a possibility with regards to the sum of the pair, okay, the pair. Now, we will be focusing on these, however, okay? So the perfect square sum could be a perfect square sum of 1, 4, 9, 16, or 25. But, let's also think about this right here. Is it really possible for two numbers to be added together, two integers to be added together, two positive integers to be added together, and give you a 1? That is impossible. Because even if you took the two smallest integer numbers, 1 through 18, it would be 1 plus 2, and that's 3, and that's greater than 1. So in reality, we're just looking at these, okay? We're just looking at 4, 9, 16, and 25. These are all the potential perfect square sums that you could get from integers numbered 1 through 18. I think I'm just going to erase this whole thing, actually, just to make it really neat, nice and neat. So the perfect square sums that we could be aiming for are 4, 9, 16, and 25. Now, we know there's going to be 9 pairs of students because there's 18 total students. So I'm actually going to just number 1 through 9 here, okay? And we know that the student who's assigned the number 1 is going to be paired with somebody. The student who's assigned the number 2 is going to be paired with somebody, etc. So all of these, let's just call them students, are going to be paired with somebody. So we're going to make a little chart with regards to the possibilities that are there for us with regards to pairing these numbers with somebody else, okay? Now, we'll start at the top, that's fine. 1 could be paired with 3 because 1 plus 3 is 4. And 1 could also be paired with 8 because 1 plus 8 is 9. 1 could be paired with 15 because 1 plus 15 is 16. But 1 could not be paired with 24 to give us 25 because there isn't a number 24, right? That we're looking at all the numbers 1 through 18. So 1 could not be paired with 24 because there isn't a 24 in this range, okay? So it is the case that 1 could only be paired with one of these at the end of the day, but in order to figure out which one, we have to kind of go through all the possibilities. So with regards to problem number, or the student who is given the number 2, well, you might want to say to yourself, well, 2 plus 2 is 4, so let me put 2 here. But the student can't be paired with himself, right, or herself. So we do have to focus on the next perfect square. So 2 plus 7 would give you 9. 2, we'll keep this in red, 2 plus 14 would give you 16. 2 plus 23 would give you 25, but that wouldn't work, right? Okay, looking at this one here, 3. So 3 plus 1 would give you 4. 3 plus 6 would give you 9. 3 plus 13 would give you 16. And we don't have to worry about 25 because 3 plus 22 would give us 25. And once again, our range is all the numbers between 1 and 18. And 4 plus 0 would give you 4, but 0 is not an option, so 4 plus 5 would give us 9. 4 plus 12 would give us 16. And 4 plus 21 would give us 25, but once again, we don't have a 21. So 5 plus 4 would give us 9. 5 plus 11 would give us 16. 5 plus 20 would give us 25, but 20 is too high. 6 plus 3 would give us 9. 6 plus 10 would give us 16. 6 plus 19 would give us 25. But again, we don't have a 19. We have an 18, but not a 19. So 7 plus 2 would give us a 9. 7 plus 9 would give us a 16. And 7 plus an 18 would give us that 25. So that's interesting. This is the first time we're seeing 18 here. So 8 plus 1 would most definitely give us 9. 8 plus another 8 would give us 16, but we don't have the opportunity to add a number to itself here. Every student is given one and only one number. 8 plus, it looks like 17 would give us 25. And yeah, that's it. So then we have 9 plus 7 would give us 16, and 9 plus looks like it would be 9 plus 16 would give us 25. Okay, so that was, quite a journey. But then you might be wondering, okay, well, we have all these possibilities, so how do we know which one is the proper pair to pair with 9? Well, the bottom line is every number 1 through 18 needs to be represented, right, in this sort of structure, right? Because every number 1 through 18 got paired with somebody else. Now, it is the case that 16 only shows up in this row. Notice how 16 doesn't show up anywhere else here. So that means that 16 has to be the one that's paired with 9, okay? Similarly, 17 does not show up anywhere else. So what that means is 17 has to be the one that's paired with 8. Looks like 18 is not paired with anything else, so therefore 18 has to be paired with 7. Now, let's see. Looks like 10 is not showing up elsewhere either. Now 3 is showing up here, right? So 3 has showed up, but 10 needs to be represented somewhere in this thing. So we can understand that 10 has to be paired with 6. Similarly, 11 is not showing up anywhere other than here, so we're going to circle that. 12 is not showing up anywhere other than here. It does indeed look like 13 is only showing up here. Like, I don't see any other 13s around here, do you? I don't see any. And then we have 14 only showing up here. And then we have 15 only showing up here. There's no other 15 in sight. So in other words, the only place where 15 gets represented according to our sort of parameters is in this top row where 15 is paired with 1. So we could ignore this because that shows up in multiple places, right? 3 shows up there, shows up there, shows up here. 8 shows up in multiple places. If for no other reason than it's right here. 1 shows up, in this column. 6 shows up in this column, right? So these are the only spots where the green numbers, are placed in the only position that they could be placed. So therefore, we're done. Anyway, I think you probably get it. Kind of a weird one, huh? Kind of a weird one. So the only number that 1 could therefore be paired with is 15. Now, some of you may have thought, well, 1 could be paired with 3 and 8, so how do I know which one? Well, this is one way of knowing which possibility you have to go with based off of the parameters. So the answer to this one is therefore B. So problem number 52 is a somewhat tricky algebra problem that features a lot of substitution. So I can already tell I'm going to need room. So let's set up the first equation based off of the first sentence. Lucky found $8.25 in pennies, nickels, dimes, and quarters while walking home from school in 1 week. So already that you know, information could be represented as the following equation. First of all, let's make sure that we know that the following is true. So we're going to say that P represents the amount of pennies Lucky has, N represents the amount of nickels Lucky has, and D represents the amount of dimes Lucky has, and Q represents the amount of quarters Lucky has. And we're just going to kind of set that information off to the side and set up the equation that I was talking about. And basically the equation is, it's going to be, let's actually put $8.25 just in terms of cents. So hopefully everyone understands that $8.25, that really equals literally 825 cents. Now, what I'm going to do is I'm going to avoid using decimals in this problem because to me, decimals can be confusing. And just put everything in terms of actual cents, okay? And we're allowed to do that. I mean, essentially, we would just be multiplying everything by 100, and therefore we're dealing with 825 cents. So the bottom line is, as far as the special equation that we could write, it would be that 1 cent times P, which is 1 cent times the amount of pennies Lucky has, plus 5 cents times the amount of nickels Lucky has, plus 10 cents times the amount of dimes Lucky has, plus 25 cents times the amount of quarters. That's all going to equal 825 cents, okay, also known as $8.25. So that's something to, definitely consider right out the gate. Then the problem gives you all of this sort of additional information that can be really, really confusing. So I'm just going to show you how I work through this kind of stuff in my head. You just take one statement at a time and just be super careful, just be super meticulous with it. So for example, when she deposited this money in the bank, she noticed she had twice as many nickels as pennies. So already the problem is mentioning a relationship between nickels and pennies. So what I'm going to do is I'm just going to write an N and I'm just going to write a P. And I know that there's some relationship there, so I'm going to write an equal sign. Then I pause and just think about it. Twice as many nickels as pennies, which means that there's more nickels here, which means that that has to be 2, okay? So you have to be super meticulous with that. N equals 2 times the amount of pennies, okay? So if it says that Lucky has twice the amount of nickels as pennies, that means N equals 2p, okay? The next statement says she noticed she had twice as many nickels as pennies. I already said that. 1 fewer dime than nickel. So apparently there's a relationship between dimes and nickels as well. So we're going to write D, we're going to write n because I know that there's a relationship between the two. I'm going to write a little equal sign, and we're going to think about it. One fewer dime than nickels. So that means there's less dimes than nickels. In fact, there's one fewer. So it's going to be n minus 1. Okay, so you have the amount of nickels, and then if you were to subtract 1, well, that's how many dimes you have. Okay, so that's that. And then finally, they say one more quarter than nickels. So once again, I'm just going to write Q. I'm going to write N. I'm going to put an equal in between them and then just look at it. So it says one more quarter than nickels. So that means Q equals N plus 1. Okay, you have a certain amount of nickels, and if you were to add one more to that, well, that's how many quarters you have. Okay, so that's how you navigate those equations, and those are very important equations. The final question is, how many quarters did Lucky find that week? So the key to solving this problem is to refer to the above equation that we constructed, and we want to solve for Q, which means we have to change each of these variables, D, N, and P, in terms of Q. Okay, we need to figure out what D is in terms of Q. We have to figure out what N is in terms of Q. We have to find out what P is in terms of Q. And once we could, once we do that, then we can just, solve for Q. So that's a tricky one, right? Well, one thing we can immediately see out the gate is that we can totally find out what N is in terms of Q by subtracting 1 from both sides. So imagine we did that. We would end up realizing that really N equals Q minus 1. That's an equation that we could definitely work with. Okay, I'm going to do little dividers here because we really have like 3 equations here. We're going to work with each one. But as it pertains to this first Q equals N plus 1, we could turn it into that, and therefore we know that N equals Q minus 1. So what that means is anytime I see an N, I can replace it with a Q minus 1. So let's actually do that over here because we want to find out what dimes are in terms of quarters as well. So if we replaced N with Q minus 1, then we could easily see what dimes are in terms of quarters. So let's go ahead and replace this N with Q minus 1. So I just did that. I just replaced N with Q minus 1, and then I actually simplified it. So D actually equals Q minus 2, and I think we should wrap that in a yellow rectangle just to draw attention to it because we're going to be using that. So now we know that N equals Q minus 1. We know that D equals Q minus 2. Well, what about this one? Well, the key to sort of figuring out what P is in terms of Q is simply to replace this N with Q minus 1 because we already know that N equals Q minus 1. So we're going to do that right now. So I did that, but let's look at this real quick. I replaced N with Q minus 1. But then we want to solve for P, so I divided both sides by 2, and we end up with P equals Q minus 1 over 2, and then I wrapped that yellow box around it. So we're going to use all the equations that are in the yellow box and bring them into this problem. So let's start with P. P we know is equal to Q minus 1 over 2, so we could just simply write that. And then we're going to be adding 5 times N, so it's going to be plus 5 times, well, what is N? N is Q minus 1, so we must put that in parentheses, Q minus 1. And then it's going to be plus 10 times D, so it's going to be plus 10 times whatever D is in terms of Q. Well, we already discovered that D equals Q minus 2, so we're going to write Q minus 2. And then after that, we just have plus 25Q, so what's great is that you don't even have to write anything here except 25Q because it already has a Q in there. So we're actually good there. And that equals 825. 825 cents to be specific. Now, we have an annoying denominator of 2 happening right now, and I don't like it. So I want to get rid of it. I'm going to get rid of that annoying denominator of 2. And the way that I'm going to do that is multiply literally both sides of the equation by 2. Okay? And you're going to see why in a moment. But let's focus on the right-hand side because that one's kind of easy. That's going to turn into 1650. Okay? Now, let's analyze what happens over here. That's going to distribute there, 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 and there. Okay? The 2 is going to distribute to all of these places. So let's analyze what happens each time. When 2 gets distributed to this one, the 2's are going to cancel, and it's just going to leave us with q minus 1. When the 2 distributes here, you want to be careful. 2 only multiplies to that 5. You have to be super careful. You don't want to go 2 times 5 and that thing. You pick one of these two numbers. You have two numbers. You have 5 and you have q minus 1. Q minus 1 is just a number. It's a quantity. You just pick one of those two to multiply 2 to. And in this case, it's going to be easier for us to multiply 2 to 5. And then we have to actually preserve q minus 1. So you do have to be careful with that. 2 times 5 times the quantity of q minus 1 is going to turn out to be plus 10 times that quantity. Notice how q minus 1 is preserved. Now we have 2 times 10 times the quantity of q minus 2. Well, that's going to be plus 20 q minus 2. And then we're going to have 2 times 25q, and that's very clearly 50q. So we have q minus 1 plus 10 times q minus 1 plus 20 times q minus 2 plus 50q equals 1650. Now that is a lot of information. It could be a little confusing, but at least now we only have one variable, and it's the variable that we want to solve for. It's the variable that 52 is asking about, problem number 52. So that certainly means that we're on the right track. Now at this point, there's not much we could do to simplify this, but let's distribute the 10 into this quantity. Let's distribute the 20 into this quantity because that's what PEMDAS says we should do. Before we add any of this stuff or combine like terms, if there's an opportunity to multiply something, we're going to want to do that. We do have an opportunity to multiply something. We could distribute the 10 here. We could distribute the 20 there. So I'm just going to sort of rewrite this equation where it's q minus 1 plus 10q minus 10 after distributing plus 20q minus 40 plus 50q, and that's going to equal 1650. I like to draw attention to the like terms. So for example, I'm going to put a blue underline under all the terms that have q in it. That way I can very easily combine those. So let's look at that. Q plus 10q is going to be 11q, plus 20q is going to be 31q, plus 50q is going to be 81q. 81q. Now all the terms that don't have an underline underneath it, I'm going to combine those. So we have negative 1 plus negative 10 is negative 11 plus negative 40 is negative 51. So it's just going to be 81q minus 51, and that's going to equal 1650. So at this point, of course, we're going to have to add 51 to both sides. I'll denote that right now. And what we have as a result is 81q equals 1650 plus 51. Now that is 1701. All right, now I know that that's 1,701, but I like to just say it like that's easier on my brain to just say the numbers. So at this point, as many of you at home know, you would have to divide both sides by 81. And then, believe it or not, you are going to have the answer. The answer is, that's an arrow, the answer is Q equals 21. And that is answer choice J. So that's how you do problem number 52. So problem number 53 relies on you remembering that anything raised to the 0 power equals 1. So if they say something like the following. If they say something like 10 raised to the 2x minus 1 over x, and that equals 1, well then this exponent has to be 0, because the only exponent that you could raise 10 to and get a result of 1 is the exponent of 0. So what's kind of cool about this is you could just forget about the 10 and you could forget about the 1 and just work with this exponent. I mean, the bottom line is we know that 2x minus 1 all over x equals 0. Now, I'll kind of throw a little bit of fancy reasoning at you guys right now, because basically, um, first of all, we know that x cannot be 0. Okay, so that's, certainly true of this problem, because if x was 0, then it would be undefined. So we have to assume that x is some number other than 0. Okay, we have to assume that it's some number other than 0. And have you noticed that, like, let's say you have a denominator of 3, anytime you have a 0 in the numerator, well, that equals 0. And this is just an example, right? Anytime you have a numerator of 0, it turns into 0. Okay, as long as the denominator is not 0 and therefore undefined. So you could have any numerator down here. It doesn't even matter what the numerator is, or the denominator rather. You could have any denominator down here. It doesn't even matter what the denominator is. As long as that numerator is 0, well, the whole thing's equal to 0. In fact, that's the only way that this fraction could be equal to 0. Okay, so therefore, in a way, we could just simplify this equation, the green equation, even more by not even worrying about that denominator and just sticking the numerator equal to 0. Okay, now some of you might be noticing, well, we could have also multiplied both sides by x and it would have turned into 0. So that's true. So solving this equation very simply would give us, let's see, adding 1 to both sides would give us 2x equals 1, and dividing both sides by 2 would give us x equals 1/2. And that is the answer. It is C. Problem number 54 asks, according to the results, what's the probability that a randomly selected person who was surveyed likes to read, given that the person plays a musical instrument? Okay, so anytime they use that phrase, given that, that means you want to focus on only one part of the table. All right, so I'm going to say that again. Anytime they say the phrase, given that, that means you want to focus on only a particular part of the table. Now, how do you know which part to focus on? Well, it's going to be the information that follows the phrase, given that. Okay? So they say, given that the person plays a musical instrument. So that means we are only focusing on this part right here. So whenever they use the phrase given that, they're about to tell you, we could say, the population that we're focused on. And this population has a total of 90 people. Now we want to know what's the probability that a randomly selected person likes to read, in this structure, given that they are one of these people. Well, that is this particular cell right there. So that will be a probability of, you can think of as part over whole. The probability in this case, you can also think of it as desired over possible, but, really works in both ways. So this would be 50 over 90, which reduces to 5 over 9, and that is G. So that's the probability, given that we're looking at this column. So problem number 55 requires you to understand a lot of different concepts, unfortunately. For example, you're going to need to know that the rate times time equals distance if you're ever dealing with like an average speed problem or whatever, or really just most problems that feature speed and distance. That's going to come into play in this particular problem. Also, it's helpful to know that, well, it's crucial really to know that the um, circumference of a circle is 2 pi times the radius Some people like to think of that as pi times the diameter as well. And that's actually a good way of thinking about it because 2 times r is the diameter, so it makes sense. It's going to be the diameter times pi. We're actually going to use this definition in this problem here. So just to kind of refamiliarize yourself with that. Another thing worth noting as well is the following phenomenon that really, as far as I could tell, does not get discussed that much in geometry class. And that is the following. We're going to put this here for reference. If you have a wheel and you have a certain circumference, let's say the circumference of the wheel is 10 inches. Okay, now this has nothing to do with the actual problem as far as the numbers, but the concept definitely applies. So imagine the circumference is 10 inches, meaning it goes 10 inches all the way around. Well, if you do a full revolution of the wheel, if you do a full revolution of the wheel and you end up here, and it's just a single revolution, well, you have just traveled 10 inches, okay? 10 inches. So, in other words, the distance traveled by a full revolution of a wheel, one full revolution, is the circumference of the wheel. So I'll say that again. The distance traveled by one full revolution of a wheel is the circumference of the wheel. So as you can see, it went 10 inches and the circumference is 10 inches. Now that's just one full revolution. Now if there's 200 of these revolutions, well, this wheel is going to travel 200 times 10, and therefore it would travel 2,000 inches. Okay, so that's important to understand. And it turns out that in this problem, you're also going to have to be fairly skilled when it comes to unit conversion, which we're going to get to soon. Okay. So, in my opinion, that's what makes this a difficult problem, is because you have all these concepts packed into a single problem. You have circumference, you have rate times time equals distance. You need the insight that one full revolution, the distance traveled by one full revolution of a wheel, is equal to the circumference of the wheel. You're also going to need to be skilled with unit conversion. So that's already like 4 things in there. Okay, now we're going to leave these here for just reference for now. So at the end of the day, we want to know at what average speed in feet per second was Mario riding during that minute. Many of you can see that one of the issues is that we don't have feet per second. I mean, we have minutes and we have inches. I mean, the problem provides us with inches and minutes. Um, so, seeing as how the final question, nonetheless, is asking about average speed in feet per second, well, it's like, okay, we don't have feet per second, but let's find the average speed in as it pertains to inches and minutes. Okay, let's just start there. If we could find the average speed of inches per minute, then we can start to think about the average speed in feet per second by doing a unit conversion. So once again, the plan is to just find the speed for Mario's bicycle riding in inches per minute, because that's what they give us, and then we'll convert it later. So how can you find Mario's speed in inches per minute? Well, the speed is r, okay? And the time that he traveled was 1 minute. Okay, so I'm just going to write 1 minute. All right, just write 1 min. But what is the distance that he traveled? What is the distance he traveled? Well, the distance he traveled was 200 revolutions. But what is that distance? 200 revolutions. Well, do you remember how I said that there's an interesting relation between the circumference of a wheel and how far it travels in terms of distance? Well, that's going to be the case with this problem, where we will indeed find the circumference of Mario's wheel based off of the diameter that they give us. Now, apparently, the diameter of the wheel is 26 inches. Okay, 26 inches. And as I had mentioned before, the circumference is equal to pi times the diameter. So we will then say that the circumference of Mario's wheel, C sub m, is going to be 26 inches times pi. So in reality, it's 26 pi inches. Okay, 26 pi inches. So that's the circumference of his wheel. Now, we also know that he traveled 200 revolutions. Okay. Now, do you remember how I said that the distance traveled by one revolution is equal to the circumference? So if he was to travel one revolution with the wheel, then he would have traveled 26 pi inches. But he didn't travel one revolution. He traveled 200 of those. So the distance traveled will be 200 times the circumference of his wheel. So I'm actually going to go ahead and write that immediately in this equation. So the distance, right, is going to go right here. And that is going to be 200 times the circumference, which is 26 pi inches. Okay. And that's going to be huge. Okay, because now we can find at least the speed, also known as the rate. We can find the rate at least in inches per minute, and then we'll just convert that to feet per second later, and then we'll have our answer. Okay, so we're finding the speed of inches per minute. Well, in order to do that, we have to solve for r, which means get r by itself, and obviously that's going to be a matter of dividing both sides by this 1 minute thing right here. 1 minute. And that, of course, would cancel these. And then we would have r equals, let's kind of work this out right now. 200 times 26 pi, that's going to be 5,200 pi. 5,200 pi. So again, 200 times 26 pi, hopefully I said that correctly. 200 times 26 pi is 5,200 pi, and that's inches on top. So I'm going to write, I'll just write IN for inches, all over 1 minute. Okay, so we know that the rate that he's traveling, the speed, is literally 5,200 pi inches per minute. That's the speed. So then now you might be wondering, okay, well, how do we convert this speed into feet per second? I'm a big fan of using this sort of grid system when doing unit conversions. It's a beautiful way to just keep the information organized. So you just draw a couple of these. It might be too much. I mean, we'll see. It might be too much, but let's just be very clear. This person travels, 5,200 pi inches per minute. So I'm going to write 5,200 pi, and we're going to have the word inch here over 1 with the word minute, okay? Now, when it comes to unit conversion, writing not only the numbers, but also the words are really important. So we have inches and minutes. So the presence of the words is crucial, okay? So from there, we need to realize, well, in the final answer, we don't want the word minute and we don't want the word inches in there, right? So we have to set things up across this whole thing in such a way that would enable us to cancel these words. Not necessarily the numbers, but we want to cancel these words out. And this is something that over time can even become fun once you get the hang of it. Okay, there's something satisfying about it actually. At the end of the day, our goal is to get rid of inches and minutes and to replace them with feet and seconds. Okay, so what we need to do is brainstorm, well, what are some of the relationships between minutes and feet and seconds and inches and feet and seconds. Well, right away, you can see that there's certainly a relationship between minutes and seconds. So what we're going to do now is just force the word minute to be up here. And the reason for that is because I'm going to want to cancel these. So you have to do, when you do these cancellations, they have to be diagonal from each other in order to cancel them. So I definitely can foresee that there is a relationship between minutes and seconds. I want to cancel the word minutes, not necessarily a number, but the word itself. So I'm going to put the word minute in that diagonal position right there. And then I ask myself, okay, well, what is the relationship between minutes and seconds? Well, obviously, there is 1 minute corresponding with every 60 seconds. So I'm going to write SEC for that, okay? Now, I am going to cancel the word minutes, but not yet. Let's fill out the rest of the table first. We know that they will cancel though, for sure. We also want the word feet in there, not inches, so we got to find a way to cancel inches out. Clearly, there's a relationship between feet and inches, so I am prepared right now to immediately put the word inches down here, and I'm just going to do IN. And just remind myself, well, most definitely 12 inches correspond with every 1 single foot. Now, what I've done is I have set the table up in such a way that the words that I want to cancel will cancel, and the words that I want to remain will remain. And let's see what that looks like actually. So that would look like this word inch crossing out or canceling with this word inch. Notice how I'm not canceling the numbers. I'm only canceling the words. And it would also be the case that the word minute would cancel with that word minute. So at this point, we've done the cancellation process where the word inches have been canceled and the word minute, the words minutes or whatever, have been canceled, okay? And now only the word feet and second remain. That's progress. At this point, all you have to do is multiply straight across. So when we multiply straight across, I'll actually get rid of this part. We don't really need that part. Once we multiply straight across, it's going to be a fraction, right? It's going to be a fraction. It's going to be 5,200 times 1 times 1, 5,200 pi, I should say. So that's 5,200 pi all over 1 times 60 times 12. Well, that is 720. Now, what you might want to do is just work with the numbers first, set up a nice fraction, okay? And then bring the sort of words in off to the side, the remaining words. I will put feet in green over seconds in blue because the word feet in the table was green and the word seconds was blue. So in a way, this is the answer, 5,200 pi over 720 feet per second. That's the answer. However, obviously that does not show up. Well, the good news is that 5,200 pi over 720 can be reduced to 65 over 9, okay? Now, let me just rewrite that as 65 pi over 9 feet per second, okay? Now, some of you might be wondering, okay, well, the pi is on top, but in answer choice A, the pi is off to the side. Well, that is actually okay. All right, let's just be very clear. So the answer, by the way, is A, in case you haven't noticed. Let's be very clear that this is equal to 65 over 9 with a pi hanging off to the side, okay? Because the reality is there's secretly a 1 underneath that pi. So it's really 65 over 9 times pi over 1. Okay, so I'll say that again. It's really 65 over 9 times pi over 1. And another way of representing that is this, 65 over 9 times pi over 1, because, every number has secretly a 1 underneath. So if you have multiplication in the numerator, just know that one of those numbers that's being multiplied on top could be sort of represented as hanging off to the side like that. And just to be thorough, I'll also continue to write feet per second. Okay. Now let's be very clear though, this is the number. Okay. It's this amount of feet per second. Okay. So that is how you do that one. Okay. So again, I want to make clear 65 pi feet per 9 seconds is the same thing as 65 over 9 pi feet per second. All right. So just take a look at this, and just realize that these are actually saying the same thing. And the final answer is 65 over 9 pi, which is answer choice A. Problem number 57 is deceptively easy because the truth of the matter is if you have an arithmetic sequence, for example, let's say the first term is 3, let's say the next term is 5, so everything goes up by 2. Let's imagine that. 9 and then 11. And let's say we have, 5 terms or what have you. Well, clearly the median would be the middle number. It would be 7. Now, I'll just tell you right now, I mean, when it comes to arithmetic sequences, the mean, or the median rather, will always actually equal the mean. Okay, that's not true for any list of numbers, but it's definitely true for an arithmetic sequence. So the median and the mean will always be the same if it's the case that these numbers are spaced apart, by the same amount of units, also known as an arithmetic sequence. Okay, so therefore, the answer to problem number 57 is A, because they already tell us that there is a finite arithmetic sequence. It's got 7 terms. They give you this extra information of saying, oh, the first term is 3/4, and they want to know what's the difference between the mean and median. Well, the mean and median are the same because it's an arithmetic sequence. So since the mean and median are the same, the difference between them is 0 because any number minus itself will be 0. Now, I understand that some of you might be wondering, what if it wasn't like a weird trick question like that? What if it was like a real problem? And some of you might not be wondering that. Okay, some of you might be happy that, oh, okay, that's the answer, moving on. So for those of you who want to move on, I totally invite you to do so. But since we're on the topic, for those of you who would like to maybe have a quick sample problem when it comes to arithmetic sequences, I'm just going to throw one in there for you right now. Okay, let's imagine we have 7 numbers and they are all numbers in an arithmetic sequence. So that is 5, 6, 7. Let's say that the first number is 70, and we will say that the last number is, let's get a little crazy, the last number is 950, okay? And what they want to know is, what is the median of these 7 numbers, okay? What is the median of these 7 numbers? So how could you go about that in a way that would be systematic, well organized, and efficient? That's the question. Well, the way to go about arithmetic sequence problems is to use this formula that says a sub n equals a sub 1 plus n minus 1 times d. Okay, now let's be very clear. Let's actually start here. A sub 1 is the first term. Okay, so in this case, it would be 70. All right, let's make clear that that's definitely a 0 right there. So a sub 1 would be 70. D is the space in between each number. So if the next term in the sequence is 74, well, the difference between this term and that term is 4, and therefore D is 4, okay? And that's actually the feature of an arithmetic sequence. An arithmetic sequence is a list of numbers that go up by the same amount each time, or go down by the same amount each time. One way or the other, you're adding the same number to each successive term to get to the next term. So D represents that number. Now, we don't know what D is here just yet, okay? We do know that A sub 1 is 70. So that leads to the question of, well, what about n? We have an n over here, we have an n over there. What does n mean? Well, let's focus actually here. A sub n, what that means is the nth term. So for example, this is the fourth term. So this is called A sub 4. So if we want to find the fourth term, which by the way we do, you would write A sub 4 equals A sub 1 plus 4 minus 1d, okay? Now, I actually think we should go ahead and flesh this out because at the end of the day, isn't that what we're trying to find? We're trying to find A sub 4. So I'm going to write A sub 4 equals 70 because that's A sub 1 plus 4. We'll put 4 in blue right now just to kind of color code things. 4 minus 1, and it's still times d. So obviously this is going to become 3, but this is the equation that would allow us to find A sub 4, also known as this fourth term. This is the equation. So we can clearly see that the roadblock is that we don't have D. So we have to go on a separate mission called find D. Figure out what D is, okay? Because if we had D, it'd be easy. It'd be 70 plus 3 times D, and then we'd have our answer, literally, because that's what we're trying to find. In fact, I'm going to put a question mark right there. That's what we're trying to find, A sub 4. So the question is, well, how do you find D? Well, what you could do is you could actually use the same equation, but plug in pieces of information that have already been given. So for example, we have things like the first term, and we have this term here. Now, what term is this? This is 1, 2, 3, 4, 5, 6, 7. So that's the seventh term, also known as A sub 7. Now, what we're going to do here is we're going to work with this term. A sub 7 turns out to be literally 950. Okay? We also know that A sub 7 equals A sub 1 plus n minus 1d, but we already have A sub 1. It's 70 plus n minus 1. So the 7, I'll write in blue down there. It's going to be 7 minus 1 times d. Okay? So really A sub 7 equals 950, and that also equals 70 plus 7 minus 1d. So what we could do is just sort of, ignore this part and recognize that 950 equals 70 plus 7 minus 1 times d. And therefore, we can solve for d. So on the next line, it would be 950 equals 70 plus 6 times d. And 950 minus 70 is 880. So 880 equals 6 times d. And then we would have to divide both sides by 6 to get d equals 440 divided by 3, or over 3. So that is a terrible looking number, but that's what you get sometimes when you make up problems on the fly like this. You're going to end up with weird numbers, but this could be a decimal, but we're going to leave it in this improper fraction form. So one way or the other, we have our d, which is great. And I'm actually seeing a cool cancellation that's going to occur. So we have A sub 4 equals 70 plus, let's just get this over with, because ultimately our goal is to find A sub 4, right? Now we have D, so that's all we needed. So A sub 4 equals 70 plus, that's going to be 3 times D, right? So it's plus 3 times whatever D is. Well, we have D. It's right here. That's D right there. 440 over 3. And what do you know? The 3's cancel, which is great. So therefore, A sub 4 equals 70 plus 440. And that equals 510. Okay, so that is an example of an arithmetic sequence problem, and we just figured out what A sub 4 is. We knew that it was an arithmetic sequence. We knew the first term, we knew the last term. turned out that's all the information we needed. Just the fact that it's an arithmetic sequence, we have the first term, we have the last term. Now this could have been any term here. Had we had a number for a sub 6, well then we would have gone through the motions over here only with a sub 6, and that would have been 6 minus 1 times d. So hopefully that makes sense. Anyway, the answer to problem number 57 on the ACT practice test is A, just to reiterate. Problem number 58 can be very intimidating because the answer choices feature trig functions. It could very well be the case you're not familiar with those or not familiar enough with them to feel confident. And there also is mention of arc lengths and so on. So there definitely is a lot going on here. I think when in doubt, when perhaps feeling overwhelmed by the information, it's probably going to be helpful to focus very closely on the final question. So the final question is, when angle ADC is measured in degrees, which of the following expressions represents the length of the arc AC? Now, let's be very clear. Arc length, okay, arc length over the entire circumference is proportional to the central angle, and in this case it's in degrees, over 360 degrees. So we know that the arc length that we're looking for is the arc AC, and that's going to be all over the circumference, which by the way is 2 times pi times r. Now we have the radius, by the way, it's 4, okay, and that's going to equal the central angle. I'm going to call that n, okay, we'll call that n degrees, central angle n degrees. So the central angle, n degrees over 360. And in a way, I kind of feel like we're getting closer to the answer because, yeah, we don't know what n is, but, there's only 2 unknowns, whereas we definitely know these. I mean, that's going to be 8 pi. So I'm actually just going to sort of rewrite it again so that we can very clearly see we have 8 pi down here, and then we have our n degrees, which we don't know what the heck that is, but we have our 360, we do know what that is, right? And at the end of the day, they're asking for AC, right? So my thought is, even if we don't quite know exactly what to do, we could at least solve AC in terms of everything else. And the way that you could do that is by simply, we'll put the result here, but what we're going to do is we're going to multiply both sides by 8 pi, because that would cancel that 8 pi. And that would leave us with AC, arc AC, equals n degrees times 8 pi over 360 degrees. Now, even though up to this point it still might be a little confusing, I think the main point is we're actually really close to solving the problem. I mean, we have arc AC equals this stuff, right? Well, we could kind of mess with this. It looks like this is going to reduce a little bit, and hopefully it's becoming clear now that soon all we're going to need is figure out what n is, and then we'll actually be done with the answer. So the truth of the matter is that 8 and 360 could reduce to 1 over 45 degrees. So I'm going to write that on the next line. So we have arc AC is equal to n degrees times, we could say, pi over 45. Now, I'm writing it this way because I'm sort of separating this out, okay? Now, the truth is, you could represent this as n times pi all over 45, or you could have n times pi over 45 off to the side, because it actually doesn't matter, because the truth is you have this sort of invisible 1 there. So we could separate it out like this, or we could just put n times pi all over 45. But I'm going to do it this way, and the reason why I'm choosing to do it this way is because when I look at the answer choices, it does seem like pi over 45 is like sort of separated out from something else, okay? Now, looking at answer choice F and G in particular, those are the ones that look really tempting, right? When you look at answer choice F, it's like pi over 45 times blah, right? And then in answer choice G, it's like pi over 45 times blah, right? Now, the blah part is weird looking and crazy, and we're going to look at that in a moment. But I don't know. I feel like it's safe to say that really what we got is arc AC equals pi over 45 times, well, n degrees, right? And the question is, what is n degrees? That's the question. Okay. In other words, what is the central angle? Okay. Now, some of you who maybe aren't really sure even what a central angle is, that's fine. I'm going to draw this thing right now. So we got a circle. We got point D in the middle. We've got C here. We've got A here. We've got this thing that drops down like that. That is of length 4. And this point is B. And that's 90 degrees, okay? So the central angle is this right here. That's n degrees. Okay, so what we are doing is we're sort of analyzing what is this central angle here. And there must be a way to figure it out. There must be a way to figure it out. And it turns out there is a way to figure it out because they also tell you that this side length is 1. Now, let's pause and take a deep breath and go on a little tour of some trig concepts. Now, I'm going to kind of talk about this, assuming the listener maybe has never heard of any of this stuff. Okay, so it is going to be a little bit of a crash course. When you have a right triangle, and maybe you have some angle here, and we'll call it n. Well, what we do is we call this side that's across from the angle, we call that the opposite side. We call this the hypotenuse, and we call this the adjacent. Now you can think of the adjacent as right next door. The word adjacent kind of means right next door, okay, or attached to or something. So it doesn't really mean next door. It means attached to or leaning up against or something, okay. Opposite is a little bit self-explanatory. You have your angle and you have to go all the way across the triangle to get to the opposite. And then we have the hypotenuse, which is the longer side, okay. That's something that is a very sort of well-known concept as it pertains to right triangles, hypotenuse. And for the record, the hypotenuse, yeah, it's the longest side, but it's also always, always, always the side that's across from the 90 degrees. But we're looking at this angle here. Now, there is this sort of trigonometric concept, trigonometry concept called SOHCAHTOA. And the SO means the sine of an angle, we'll call it angle N, is equal to the opposite over the hypotenuse. Okay, so that's the SOH, S-O-H, so. There's another concept called cosine, where the cosine of an angle n degrees is equal to adjacent over hypotenuse. Now, there's a lot to say about what this means. Just know that these are useful ratios, useful relationships with regards to the angle and the side lengths of a triangle, okay? They're just useful relationships with regards to an angle and, you know, the side lengths of a triangle, and they're all ratios. And, you know, when you take trig, it's going to become a little bit more obvious how they're useful. So I'm writing tan here because that's the next one. The TOA means that the tan of an angle N is equal to the opposite side over the adjacent. Okay, and that's where you get the O and the A from. So hopefully this is sort of coming together for you. Also, just know, you know, the corresponds with cosine, that's C-A-H. So that right there is a bit of a crash course with regards to SOHCAHTOA, a very famous concept. You might be wondering, okay, well, how does that relate exactly? Well, one thing we know for sure is that the tan, or not the tan, but there's an angle, we have an opposite side, and we have a hypotenuse, and that corresponds with sine, okay? Anytime you have an angle, an opposite side length, in this case it's 1, and a hypotenuse, in this case 4, well, that's opposite and hypotenuse. There's only one of these three trig functions that feature the opposite and the hypotenuse, and that turns out to be SOH, also known as, sine. So really we're dealing with a situation where sine of the angle n is equal to opposite over hypotenuse, which is 1/4. Okay. Now already, you might be looking at answer choice F and becoming suspicious that that's what we're dealing with. Because so far, just to reiterate, this is our sort of answer so far in the blue box, right? We did all this stuff with the arc length formula. We got AC by itself, and we put everything else over there. And then we're like, oh crap, we need that central angle N, you know what I mean? And we got to take it from here. Um, and we know that the answer is going to be, oh, it's pi over 45 probably times something else. Well, now we're talking about sine, right? So when you look at answer choice F, it's like pi over 45 times something that has to do with sine, right? So if you're running out of time, you might want to guess that one, okay? Because sine seems to be an important trig function as it relates to this problem. But you might be wondering in the answer choice, okay, well, what the heck is that weird negative exponent of 1 that's hovering above sine, and then there's the 1/4 instead of an n in there, right? This says sine n. This doesn't say sine 1/4, it says sine n. So we're going to make sense of it now. There's another concept where, let's say you don't know the angle. There's a way to find the angle. And the way to find the angle is to use an inverse trig function. And the inverse trig function, when it comes to sine, is what's called the inverse sine. Some would call it an arc sine. And what inverse sine does is, first of all, it always has this -1 hovering above it. Now, believe it or not, that's actually not an exponent. I know it looks like an exponent, but it's not. That's a symbol that says we're now doing the inverse sine. Okay, that's what it means. It's not an exponent. It's more like a code symbol that's saying this is the inverse sine as opposed to just the sine. And all you have to do is switch these things. We got n over here now, and we've got 1/4 there. So one way of thinking about it is if sine of the angle n equals 1/4, then the inverse sine of 1/4 equals the angle n. Okay, so this is a relationship. This is a visual that you need to sort of get used to, or at least be loosely aware of. If the sine of an angle equals something, then the inverse of that something is going to equal the angle. So in a way, we actually did just find out what n is equal to. N is equal to the inverse sine of 1/4. Now, some of you who are not familiar with this might be like, okay, well, how's that helpful? That's not a number. Well, actually, it is a number. This is something that if you had like a graphing calculator, even on your iPhone, if you have an iPhone, if you tilt it sideways, there are ways of actually finding the inverse of 1/4. You might want to do the inverse sine of 0.25, and that would actually give you the exact measurement of the angle. You'd have to make sure the angle is in degrees, the calculator is in degrees, just so you know, as opposed to radians. So that is the case with calculators. So this actually is a number, is what I'm trying to say. Now, the good news is you don't even need to know the number because the answer choice doesn't seem to care about what the inverse sine of 1/4 is. The answer choice just puts the inverse sine of 1/4 in for n. So basically what that means is we can replace this. I'll write the whole thing down here with the arc AC is equal to pi over 45 times not n, but the inverse sine of 1/4, because we already discovered that n equals the inverse sine of 1/4. So that is how you do that one. Okay. Definitely a tough one. I mean, there's a lot of, by the way, let's answer choice F. There's a lot of places to potentially get confused or overwhelmed. I mean, first of all, you're presented with a ridiculous circle with a triangle, and it's a little tight over here. Maybe you're not exactly sure what's happening over here. Then you are sort of required to understand, okay, well, there's an arc length formula. Maybe that will become useful. You need to make sure you're definitely thinking about degrees. So this is 360 degrees down here. N is in degrees. You have to be proficient when it comes to getting AC, arc AC by itself, which is the arc length, right? AC by itself, you could do that by getting rid of this denominator, multiplying both sides by 8 pi. We then moved it over here, so arc AC equals all this gobbledygook. We quickly realized that the 8 pi over 360 could reduce, so we have pi over 45. And we know that n degrees times pi over 45 is, close to the answer. But then when we looked at the answer choices, we saw that it was switched. So really it's pi over 45 times n degrees. And then we knew that we are now on a mission where we have to find n degrees, and that's where all the trig functions came into play. We recognized that we didn't know the angle, but we knew that the sine of the angle is opposite over hypotenuse. So we literally just set up that equation because we knew it was true. Sine of n equals 1/4. Okay, great. And then hopefully some of you at home will remember, okay, well, whenever the angle is the mystery, whenever you don't know the angle, you could always find the angle by doing the inverse trig function and, write it, and then just make sure you switch. You put 1/4 here and you put n over here. So there's a little switcheroo that occurs there, right? And then you've effectively solved for n. You've effectively figured out, okay, that is the angle measure that is in the triangle, right? We just found the angle measure. And maybe just to know mentally that if you wanted to, you could plug that into the calculator. You're going to get some kind of a number. But as it turns out, when it comes to the answer choices in problem number 58, you don't need to do that, right? Because they just have inverse sine of 1/4. So I just recapped everything. That might be unnecessary, but it could have been helpful. So hopefully that makes sense. And yeah, answer choice F. Okay, so problem number 59 actually baits you into using that trig formula. Now that is an interesting trig formula, the whole 1/2 AB times sine C. That most definitely could be used. There's no question. Um, but I'm going to present to you a way to do this without that. So we want to find the area of the triangle, right? And here's the triangle. We know that that's 4. We know that that's 5. I don't even care about the dumb decimals. That's extra information too. The fact that they gave us the 4.0 and 5.0, totally extra information. I don't care about any of that. We also know that the entire base, if we're going to treat this as the base, is 8, right? We also know that this angle that is in there is 30. Okay. Now, before I dive in, let's just set this off to the side and remember something. I want you to just temporarily forget this. Let's remember something though. There's a special right triangle called a 30, 60, 90. And this right triangle is always such that the short leg is some number, we'll call it A. The hypotenuse will always be twice that. We'll call that 2A. And this sort of longer leg will always, always, always be A radical 3. That's something that you should be familiar with on the ACT. You should also be familiar with 45, 45, 90 triangles. And in case you don't know what that is, just Google that. But this is called a 30, 60, 90 triangle, and that's a famous right triangle. Because if you know these relationships, then you don't even have to use the Pythagorean theorem. And let's keep in mind, A, which corresponds with the shorter leg, right? Not the hypotenuse, but the shorter leg. That's always going to be across from the 30-degree angle. And that makes sense because 30 degrees is the smaller angle. 60 is a little bigger. So 60 degrees is going to give birth in a way, or it's kind of a weird metaphor, but it's going to, I don't know, I like to think of it actually as a spotlight that's kind of shining on a wall. Like this is the flashlight over here. And the beam of light has an angle of 60 degrees, so it creates a larger spotlight on the wall, if that makes sense, or on the floor in this case. So we have A over here. So my point is that the short leg will always be across from the 30-degree angle. Now, how does that apply? Well, that applies because we have the base, and we know that if we want the area of the triangle, which, by the way, is what they're asking for, they're literally asking for the area. And then they're saying to the nearest 1 centimeter squared, like as though we have to round it or whatever. We're not going to have to round it because the bottom line is all you need to find the area of any triangle is to find the base and the height, multiply them together, and then multiply that by 1/2. Okay? Well, we have the base, don't we? It's 8. So the area of this triangle is going to be 1/2 times 8 times whatever the heck the height is. But what's the height? Well, the height is the imaginary line that would connect the top all the way to the bottom in such a way that would form 90 degrees. Now look at what we have. We have a 30, 60, 90 triangle. And in case you're not sure that that's 60, well, think about it. 30 plus 90 is 120. 180 minus those two, the sum of those two would give us 60. So we have 60 up there. This is a 30, 60, 90 triangle. And this right here is the short leg. In fact, I'm going to call it A because that's what I called it over here. Okay. Now, let's be clear. A is the height. Okay. But let's find A. Well, in a 30, 60, 90 triangle, A, the short leg, is 1/2 of the hypotenuse. So, I mean, you could think of the hypotenuse as 2 times A, but you could also think of A as 1/2 whatever this long number is, or this large number is, right? So A is 1/2 of that. So A is 2. Now keep in mind I could have called this H as well. Case could be made that maybe I should have called it H because it is the height. But I wanted to call it A to make it correspond with this A. Okay. Now, let's go to the next line, therefore, and realize that, okay, well, it's going to be the area is 1/2 times the base, which is 8, times the height, which is 2. And guess what? We're totally about to solve this one. This is going to be 1/2 times 8, which is 4 times 2, which is 8. So the area equals 8. And that is answer choice C. Now, some of you might be wondering, okay, if you're anything like me, actually, you're wondering, okay, great. So there was like a math hack that we could use to solve this problem. But what if we didn't have access to that trick? What if we had to use that terrible looking formula, 1/2 AB sine C? So I'll just tell you, for those of you who don't care and you're happy with that hack, then go ahead and move on and, leave this video now. But for those of you who are curious, okay, what would we have done had we needed to use that formula? Well, I'm going to go over that now. So let's be very clear. They gave us a triangle. I think we're clear about that. They gave us a triangle. That's 4. I'm not going to do the decimal stuff. That's 5. That's 8 and 30 degrees. Okay. And then they basically say, oh, by the way, one way of finding the area of a triangle is you could totally just be like area equals 1/2 A times B times sine C, okay? And then they kind of give you this gobbledygook, like explaining what A, B, and C are and the capital A, B, and C. I'm just going to break that down right now. Notice how A and B are lowercase. Notice how this C is big. Anytime you see a big capital letter, that means an angle measure. Anytime you see a lowercase letter, that means a side length. So for example, 30 would be denoted by a capital letter because 30 degrees is an angle measure, whereas something like 8 is a side length. So that would be denoted by a lowercase letter, okay? And they're basically saying, oh, you could totally find the area if you just use this thing. Well, the bottom line is it says sine of C, all right? We don't know the area, so it's A equals all this. If we could just fill this in with useful information, well, okay, we could just plug it into our calculator and figure it out, right? So turns out that you can. What you need to do is realize that they say sine C, which means that some angle measure is going to be involved. So already we're going to treat um, this uppercase C as 30 degrees because that's the angle measure that they gave us, okay? So before I even fill anything in, I'm going to label the triangle, and we're going to force that vertex of the triangle to be angle C, okay? And let's just go around clockwise. So this would therefore be A, and this would therefore be B. Now, it all started here because we knew that we're going to use this formula. We're going to have some angle measure here. They gave us an angle measure called 30 degrees, so why don't we go ahead and call this C, all right? We do have the freedom to do that. Now, before we move into this, let's be very clear. We have capital letter A, capital letter B, capital letter C, and each of these big capital letters correspond with an angle and an angle measure for that matter. Now, some of you have taken trig, you guys know this stuff, but some of you maybe didn't take trig, you don't know it. So you need to understand that if there's a capital letter A, well, the side that's across the triangle, the side that's opposite to that angle, well, that's going to be lowercase a. So lowercase letter a is 8. Similarly, if you have a capital letter B assigned to an angle, well, the side length that's opposite to that angle is going to be lowercase b. And of course, this, due to the same reasoning, 5 is equal to a lowercase c. Now, it turns out we actually don't need that because now we have all the information with a and b equals 4 and all that. We actually have enough information to figure this out. So what we're going to do now is we're going to rewrite it only with our new information. 1/2 times something, I'm just going to do empty parentheses, times sine of what C? 30 degrees. Okay. And here is going to be A and lowercase letter a, and that's going to be 8. So we're going to have 8 in there. And this is going to be lowercase letter b, which is 4. 4. And obviously, we're just going to multiply it all up. But you might be wondering, well, what's sine of 30? Well, sine of 30 is something that you could put into your calculator. Okay, so you could use your calculator for that. And that is actually 1/2. Okay, so what I'm going to do is rewrite this whole thing. Only instead of writing sine, sine of 30, I'm going to write 1/2. And this is still 8, and this is still 4. And really, the rest of the calculations are not that bad, right? I mean, let's just think about it. 1/2 times 8, well, that's actually 4. Right? 1/2 times 8 is 4, just looking there only. And then 4 times this 4 is 16. And then 16 times 1/2 is 8, and that would give us the answer as well. Now, just because it took me this long to explain the problem doesn't mean that it will necessarily take you that long to solve the problem, okay? It's conceivable that you could notice this, you could realize the angle that's featured is uppercase C, so the angle measure that's given needs to be assigned with that uppercase C, label it from there, label the rest of the angle and side length measures from there, and then just fill in the cast of characters and then be done with it. So that would have led to the same answer, which is answer choice C. Problem number 60 gets fancy with statistics, concepts, and terms. Some of you might not have a lot of experience with statistics in general. I will say the good news is that the statistics concepts that you need for the ACT are pretty basic. It's going to be very broad strokes stuff. And problem number 60 is actually an example of that. I understand that it says probability distribution. Well, already that's a big scary word. The discrete random variable, that's a big scary word, you know. And then you see this table that has a big X equals a small x and the fractions. It's just terrible looking. Like I totally understand that. It turns out that this is easy once you sort of have it explained to you, which I'm going to do. Okay, so basically, I'll just recreate this. So here's the table in essence. I did some dividing lines to sort of separate everything. Okay, I'm going to try to liken this to a real world situation and help you get a sense of what they're really asking for, because they're asking for the expected value, right? So the question is, okay, what does that even mean, expected value? All right, imagine that this is a game at a casino where maybe it's like one of those roulette wheels. I don't really know too much about that stuff, but imagine like a roulette wheel thing where it's like, you get a certain amount of points every time they spin the wheel. Okay, so you can imagine there's this big game and they spin the wheel, and every time they spin the wheel, you get a certain amount of points. Okay, should you continue to play the game. Okay, so you're playing this game, and every time they spin the wheel, you get a certain amount of points. Now, at any given spin of the wheel, you're either going to get 0 points after the wheel spins, you're going to get 1 point maybe for the wheel spin, maybe you're going to get 2 points that round, maybe 3 points, maybe 4 points, 5 points, or 6 points. So you can imagine probably, 6 points, that'd be amazing because they spin the wheel and it's like you just got 6 points, and that's a lot of points. Okay, so the bottom line is the probabilities over here, these are all probabilities. So this is the chances of you getting 0 points if they spin the wheel. This is the probability or the chances of you getting 1 point if they spin the wheel. This is the chances of you getting 2 points if they spin the wheel. This is the probability that you're going to get 3 points, and so on. And there's literally a 0% chance or a probability of 0 that you'll get 5 points. So apparently, getting 5 points is impossible. Okay, that's just impossible. So it's kind of funny how it shows up in the table. But maybe this table actually in reality doesn't have anything to do with a game like that, but we're going to imagine that it does. Okay. Now let's say that some person came up to you and said, it's like, okay, yeah, like they spun the wheel, you got 0 points, then maybe the next round you got 4 points on that spin, maybe on the third round you got 2 points on that spin, maybe on the fourth round you got 6 points on that spin. But what if somebody came up to you and said, okay, well, let's say you played this game forever. Let's say you played this game forever and they spun that wheel an infinite amount of times. What is the average score you would get for each spin? If you played this game forever with infinite spins, what would be the average amount of points per spin that you would earn given each probability? Okay, and that is the expected value. In other words, what is the expected value of points that you would receive per spin if you were to average things out in the final analysis? Okay, now it might be a decimal. Like it might literally be that the average amount of points you would pick up is like 3.3 points per spin. Okay, now it's literally impossible to get 3.3 points because you could either only get 0, 1, 2, 3, 4, 5, or 6 points. But when you sort of add it all up and do the expected value, it might pump out something like 3.3, which gives you an idea that you're going to get, on average, just over 3 points per spin. And then you're going to add it all up at the end, and that would be your total points. So the way to find the expected value is to simply um, multiply each of these times its probability and then add it all up. Okay, that's what you have to do. You have to multiply each of these and then add it all up. Now, what we're going to do is we're actually going to use this table. We're going to use the table to our advantage. And in fact, you might even want to do that on the ACT just to keep things organized because they already gave it to you in a relatively organized fashion. So here's a nice organized way of going about it. Now, what did I just say? I just said you're going to multiply each of these and then you're going to add it. So we're going to multiply across and put it here, and then we're going to add everything down. So let's start with 0. I'm going to do an asterisk for the multiplication symbol. Okay. And yeah, I'll just do, we'll label it properly. So it's going to be x times p, x equals little x. Okay. So 0 times 1/6, clearly that is 0. 1 times 1/12, well, clearly that is 1/12. 2 times 1/4, well, if you reduce that, that's going to turn into 1/2. 3 times 1/12, that's going to turn into 1/4. We have 4 times 1/12, that's going to turn into 1/3. 5 times 0, obviously, 0. And then finally, 6 times 1/3, well, that's going to turn into 2. Now, like I said before, we're going to be adding all of these. And I say we sum them all up and just put the total, the sum down here. Now, many of you can tell that unfortunately we do not have a common denominator. So I see this 12 right here, and everything else looks to be a factor of 12. So let's make 12 the LCD, which is the least common multiple of all of these denominators. So we're going to make 12 the target denominator. Now, we'll actually start here. So this is just going to remain 1/12. This might be weird, but I'm just going to do it for the sake of thoroughness. We're going to make it 0 over 1/12. This one obviously is going to become 6 over 1/12. And being very careful, 1/4, what is that? Well, that would be 3 over 12. 3 over 12. This one, 1/3, is 4 over 12. We once again have 0 over 12. And over here we have 2 equals 24 over 12. So if we were to add all of that up, well, certainly the denominator would be 12, right? But then looking at the numerator, 0 plus 1 is 1, plus 6 is 7, plus 3 is 10, plus 4 is 14, plus 24 is 38. Now, let's say you're pressed for time on the ACT and you just want to, you've made it this far and you're like, okay, well, I just got to throw an answer onto my answer sheet right now. Well, K is the only one that would work at this point because K is a mixed number. And this is an improper fraction. So as you know, all improper fractions could be converted into mixed numbers or, secretly are mixed numbers. It's just a different way of looking at it. And seeing as how answer choice K is the only mixed number in the answer choices, you would indeed be finished if you simply circled answer choice K. Nonetheless, I'm going to briefly review how to do that for those of y'all who may have forgotten. So 38 over 12, improper fraction, which means that it's top heavy. The numerator is larger than the denominator. And the way to handle these or turn them into mixed numbers is to treat them as the division problem that they are. I mean, truth is that all fractions are really just division problems. Yeah, it's like 38 over 12. You could see it that way, but it's really just 38 divided by 12. So let's take a look at what that actually is if we do long division. So 38 divided by 12. Well, 12 goes into 38 three times because 12 times 3 is 36. So it's going to be 12 times 3 is 36. We put 36 here. You're going to subtract that and you will get your remainder of 2. Now, it is the case that the quotient ends up giving you the large number. The remainder is always going to be the numerator, in which case, in this case, it's 2, and the divisor will always give you the denominator. And some of you might be wondering, well, that doesn't show up in the answer choices, but in reality, it kind of does because that could be rewritten as 3. And what is 2 over 12? What is 2 over 12? Well, that could be reduced to 1/6, right? So that is why the answer is K. Now, quick recap, expected value, actually not that bad. You just multiply each score times whatever the probability there is of getting that score. So each score times its own probability, and you're going to get a result. Each score times its own probability. And then after you're done with that multiplication process, then you just add up all the results, and that's going to give you the expected value. So that's how you do problem number 60.